Hello there, and welcome to the Sleepy Science channel. Tonight we'll be exploring the quiet beauty of crystals. These ancient structures formed deep within the earth over millions of years. They emerge from darkness into light, carrying stories written in their atomic patterns. Some are transparent as water, others opaque as midnight. Some sparkle with inner fire, while others glow with soft, diffused light. Crystals are both common and extraordinary, found everywhere from mountain peaks to ocean floors, yet each one is unique. If you enjoy these peaceful journeys, I invite you to like and subscribe or share a thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm beauty of crystals to carry you into sleep. Let's begin. Every crystal begins with a single seed, growing atom by atom. Deep beneath the surface, in chambers of molten rock or within water-rich cavities, the conditions become just right. Temperature drops, pressure shifts, or solutions become saturated. At that moment, a single atom or molecule settles into position, then another joins it, and another, each one locking into place according to invisible rules written in the laws of chemistry and physics. This is how crystals are born, one atom at a time, building outward in perfect geometric patterns. The process can take thousands of years or millions. A quartz crystal the size of your thumb may have grown for longer than human civilization has existed. Each face, each edge, each angle reflects this patient accumulation. When you hold a crystal, you are holding time itself, frozen into solid form. The seed that started it all may be invisible at the center, but its influence radiates outward through every layer. Crystals form when atoms arrange themselves in repeating patterns. What makes a crystal different from ordinary rock is its internal order. Atoms within a crystal are not scattered randomly, but locked into precise, repeating arrangements called lattices. Imagine a three-dimensional grid extending in all directions, each point occupied by an atom or molecule in exactly the right place. This regularity gives crystals their characteristic shapes. Salt crystals form cubes because their sodium and chlorine atoms stack in cubic patterns. Quartz forms six-sided prisms because silicon and oxygen atoms prefer that arrangement. The external shape of a crystal is a reflection of its internal architecture, geometry, made visible. Scientists can identify crystals by their angles alone, measuring the relationships between faces. Even when two crystals of the same mineral look different in size or color, their angles remain constant. This is the law of constancy of interfacial angles, discovered centuries ago. It reveals that beneath the surface, order reigns. Crystals are nature's geometry lessons, teaching us that beauty often emerges from repetition and structure. Some crystals grow in caves over millions of years. Deep underground, hidden from sunlight and human eyes, vast caves hold some of Earth's most spectacular crystals. In these silent chambers, mineral-rich water seeps through cracks and crevices, depositing dissolved substances drop by drop. Over geological timespans, crystals grow to enormous sizes. In Mexico's Cave of Crystals, selenite beams as large as tree trunks crisscross the space, some reaching over 30 feet in length. These giants formed in water heated by magma below, growing steadily for 500,000 years. The cave remained flooded, maintaining perfect conditions for uninterrupted growth. When miners drained it, they discovered a crystalline forest, unlike anything seen before. The heat inside is so intense that humans can only survive minutes without cooling suits. Yet the crystals endure, patient and silent. waiting in their underground cathedral. Other caves hold different wonders. Some are lined with delicate gypsum flowers, others with curtains of translucent calcite. Each one is a hidden gallery, carved by time and water, decorated by the slow artistry of mineral deposition. Water is often the key to crystal formation. Many crystals need water to form, acting as both solvent and transport medium. Water dissolves minerals from surrounding rock, carrying them through cracks and pores until conditions change. When the solution becomes supersaturated, perhaps because water evaporates or temperature drops, dissolved minerals can no longer remain liquid. They precipitate out, forming solid crystals. This is how geodes form, hollow rocks lined with crystals that grew inward from the walls. Water flowed through, deposited layers of minerals, and gradually filled the space with sparkling points. Some crystals form in hot springs, where mineral-laden water rises from deep underground. As it cools, silica or calcite crystallizes, building terraces and mounds over centuries. Even in the ocean, water facilitates crystal growth. Salt crystals form when seawater evaporates in shallow pools. Ice itself is a crystal, water molecules arranging into hexagonal patterns as they freeze. Without water's dissolving power and its ability to move substances, many of Earth's most beautiful crystals would never exist. Magma deep underground creates many crystals as it cools. Beneath our feet, molten rock churns and flows, heated by Earth's interior. When this magma cools, either deep underground or closer to the surface, minerals begin to crystallize. Different minerals solidify at different temperatures, forming a sequence. The first to crystallize are often olivine and pyroxene, dense minerals that sink to the bottom of magma chambers. As cooling continues, feldspars and micas form. Finally, quartz and other silica-rich minerals crystallize from what remains. This process, called fractional crystallization, sorts minerals by their melting points. Granite, one of Earth's most common rocks, is essentially a mixture of crystals that formed together as magma cooled slowly underground. The longer the cooling, the larger the crystals. Some granites contain crystals visible to the naked eye, each one interlocking with its neighbors. In pegmatites, extremely slow cooling produces enormous crystals, sometimes several feet long. These giant crystals grow because dissolved elements have time to migrate through the cooling magma, feeding growth at crystal faces. The result is mineral specimens of exceptional size and clarity, treasures from the depths. Pressure and heat deep in Earth can transform crystals into new forms. Not all crystals form from liquids or solutions. Some are born through transformation, when existing rocks and minerals are subjected to intense heat and pressure deep underground. This process, called metamorphism, rearranges atoms into new crystal structures without melting. Limestone, made of calcite crystals, can transform into marble, where calcite recrystallizes into larger, interlocking grains. Shale, a soft rock, becomes slate, then schist, and finally gneiss as pressure and temperature increase. Each stage produces new minerals and new crystal arrangements. Garnets often form during metamorphism, growing as compact, geometric crystals embedded in surrounding rock. Metamorphic crystals tend to be well formed because atoms have mobility under heat and pressure, allowing them to settle into organized patterns. The deepest metamorphism occurs dozens of kilometers underground, where temperatures reach hundreds of degrees and pressures are immense. Under such conditions, even stable minerals break down and reform. Diamonds are the ultimate metamorphic crystal. formed from carbon subjected to extreme conditions in Earth's mantle. When volcanic eruptions carry them upward, they bring pieces of the deep Earth to the surface, crystalline ambassadors from realms we can never visit. Crystals can take thousands or millions of years to form. Patience is written into every crystal face. The smallest crystals might form in days or weeks, but large, well-developed specimens require geological time. A finger-sized quartz crystal might take 10,000 years to grow. The selenite giants in Mexican caves grew over 500,000 years. Diamonds require millions of years under mantle conditions before volcanic forces bring them up. Even then, they must survive the violent journey without shattering. This slow formation means crystals are windows into deep time, each one older than forests, older than mountains, older than species. When you hold a crystal, you are touching something that formed when the world was entirely different. The continents were in different positions, the climate was warmer or colder, and different creatures roamed the land. Yet the crystal endured, growing silently in darkness, waiting for erosion or human effort to bring it to light. This perspective transforms how we see them. They are not just objects, but time capsules. Their growth rings and inclusions record changing conditions over eons. To study a crystal is to read Earth's history written in mineral form. Some crystals form in hours when conditions are perfect. While most crystals are slow-growing, some appear almost overnight. When volcanic gases rich in sulfur and other elements escape from fumaroles, they cool rapidly and crystallize within hours. Sulfur crystals can form bright yellow clusters in days. In laboratory settings, scientists can grow crystals even faster, creating gem-quality synthetic stones in weeks rather than millennia. Even in nature, certain salts crystallize quickly. After a rain in a desert, evaporating water can leave salt crystals scattered across the ground by morning. Ice crystals, snowflakes, form within minutes as water vapor freezes around dust particles high in the atmosphere. Each snowflake is a genuine crystal, with six-fold symmetry reflecting the molecular structure of ice. Though they last only briefly, they are as perfectly ordered as any gemstone. The speed of formation depends on how quickly atoms can move into position. In hot solutions or gas phases, atoms are mobile and can find their places rapidly. In solid rock or cool water, movement is sluggish and growth takes ages. Fast or slow, the process remains the same. Atoms arranging themselves into order, building beauty, one layer at a time. Each mineral has its own crystal system and characteristic shape. Mineralogists classify crystals into 7 systems based on their internal symmetry. The cubic system produces shapes with equal axes at right angles, like salt and pyrite. The tetragonal system resembles cubes, but with one axis longer or shorter. The orthorhombic system has 3 unequal axes at right angles. The monoclinic system has 2 axes at right angles and 1 inclined. The triclinic system has no right angles at all. The hexagonal and trigonal systems produce 6-sided shapes. These systems aren't arbitrary. They reflect how atoms can pack together most efficiently. Quartz belongs to the trigonal system, explaining its 6-sided prisms. Fluorite is cubic, forming perfect octahedrons when well developed. Gypsum is monoclinic, often growing as flattened blades. By observing a crystal's angles and faces, mineralogists can deduce its internal structure and often identify the mineral. This connection between inner order and outer form is one of crystallography's fundamental insights. It means that shape is not accidental but inevitable, determined by the nature of the atoms involved. Every crystal face tells a story about the forces that arranged it. The same mineral can form different-looking crystals depending on conditions. While each mineral has a preferred crystal form, growth conditions can alter appearance dramatically. Calcite normally forms rhombohedrons, slanted box shapes, but it can also grow as scalenohedrons resembling dog teeth, or as flat sheets, or as fibrous masses. These variations depend on temperature, pressure, the presence of impurities, and how quickly growth occurs. Fast growth tends to produce elongated or skeletal crystals, while slow growth allows well-proportioned forms. Impurities can poison certain crystal faces, preventing growth in some directions and favoring others. This is why quartz sometimes grows as slender needles and other times as stubby prisms. The underlying lattice remains the same, but external shape adapts to circumstances. Collectors prize unusual crystal habits, those rare forms that showcase a mineral's versatility. Twinning, where two crystals grow together in specific orientations, creates intricate shapes. Penetration twins look like one crystal passing through another. Contact twins share a face. These accidents of growth add character, making each specimen unique, even within the rigid rules of crystallography. Crystals can grow in clusters or as single perfect specimens. Some crystals prefer company, growing in clusters where many individuals share a common base. Amethyst geodes are filled with thousands of quartz crystals, all pointing inward, creating a sparkling cavity. Each crystal in the cluster grew independently, but in the same direction, influenced by the geode's shape. Other crystals grow alone, single individuals with fully developed faces on all sides. These are called eudral crystals, and they form when growth is unobstructed. A single quartz crystal sitting in a pocket of clay, fed by slow seeping solutions, can develop into a perfect hexagonal prism, terminated by pyramid faces. Such specimens are prized for their symmetry and completeness. The difference between clustered and solitary growth depends on available space and nucleation points. If many seeds form close together, a cluster results. If only one seed forms in a spacious cavity, a single crystal can flourish. Both are beautiful in different ways. Clusters dazzle with their multiplicity, each crystal catching light at a different angle. Solitary crystals impress with their geometric perfection, every face meeting at precise angles, every edge sharp and defined. Some crystals are transparent, others translucent or opaque. A crystal's relationship with light depends on its structure and composition. Transparent crystals like quartz or topaz allow light to pass through without scattering, creating a window-clear effect. You can see through them, read text behind them, watch light refract into rainbows. Translucent crystals like rose quartz or alabaster let light through but diffuse it, creating a soft glow without clarity. Opaque crystals like hematite or magnetite block light entirely, reflecting it from their surface or absorbing it. The difference lies in how atoms are arranged and whether they contain inclusions or impurities. Even tiny amounts of foreign material can scatter light, turning a transparent crystal cloudy. Air bubbles, liquid inclusions, or microscopic cracks all affect transparency. Some crystals appear transparent when thin, but opaque when thick. Others are transparent in one direction but opaque in another, a property called pleochroism. Light and crystal structure interact in complex ways, creating the infinite variety of appearances we observe. Each crystal's relationship with light is part of its character, shaping how we perceive and appreciate it. The color of crystals often comes from trace impurities. Pure quartz is colorless, as clear as glass, but add a trace of iron, and it becomes amethyst, glowing purple. Add different iron impurities, and it turns into citrine, warm and golden. Pure corundum is also colorless, but a touch of chromium creates rubies red, while iron and titanium together produce sapphires blue. These impurities replace atoms in the crystal lattice or nestle between them, altering how the crystal absorbs light. The colors we see are the wavelengths the crystal doesn't absorb. Amethyst absorbs yellow and green, reflecting purple. Ruby absorbs green and blue, reflecting red. Some crystals owe their color to radiation. Smoky quartz forms when natural radiation from surrounding rock alters the quartz structure over millennia. The color is a kind of injury, a change forced upon the crystal by its environment. Other crystals get color from inclusions, tiny crystals of other minerals trapped inside. Green quartz may owe its hue to included actinolite or chlorite. These imprisoned crystals tint their host from within, adding complexity to appearance. Color in crystals is rarely simple, often involving multiple causes working together. Some crystals change color when viewed from different angles. Certain crystals display pleochroism, showing different colors depending on the angle of observation. Iolite, for example, appears blue when viewed along one axis, but yellow or gray from another. This happens because the crystal absorbs light differently in different directions, a consequence of its internal structure. Atoms arranged in one direction interact with light differently than atoms in another orientation. Tourmaline is strongly pleochroic, often showing two distinct colors. Gem cutters must consider this when shaping stones, orienting the cut to display the most attractive color. Dichroism refers to two colors, trichroism to three. Andalusite is famously trichroic, showing yellow, green, and red, depending on direction. Under a polarizing microscope, these effects become even more pronounced, revealing the crystal's optical character. For observers, pleochroism adds a dynamic quality to crystals. They seem to shift and change as you turn them in your hand, as though alive with inner light. What appears blue becomes green, what seems yellow turns brown. This color play reminds us that crystals are not static objects, but structures that interact with light in complex, orientation-dependent ways. Certain crystals glow under ultraviolet light. Some crystals hold a secret revealed only under ultraviolet lamps. Fluorite, named for the phenomenon, often glows bright blue or green when UV light strikes it. Calcite may fluoresce red, orange, or pink. Willemite shines brilliant green. This fluorescence occurs when UV photons excite electrons to higher energy states, and the electrons release visible light as they return to normal. The glow fades immediately when the UV source is removed. Other crystals show phosphorescence, continuing to glow for seconds or minutes after the light is turned off. These crystals store energy and release it slowly. The effect is caused by trace impurities called activators, often manganese or rare earth elements. These activators trap excited electrons briefly before releasing them. Collectors enjoy shining UV lights on their specimens, revealing hidden colors invisible in daylight. A rock that looks dull in ordinary light might explode with color under UV, creating an otherworldly spectacle. This luminescence is not magic, but physics, the dance of electrons and photons within the crystal lattice. It reminds us that crystals have properties beyond what our eyes normally perceive, hidden dimensions waiting to be revealed. Some crystals are radioactive, holding energy within. Certain minerals contain radioactive elements, like uranium or thorium, incorporated into their structure. These crystals emit radiation as their atoms decay, a slow process continuing for millions of years. Uraninite, also called pitchblende, is a primary ore of uranium and was the source from which Marie Curie first isolated radium. Autunite and torbanite are uranium-bearing minerals that glow yellow, green under UV light. Though beautiful, they must be handled carefully and stored properly. The radiation they emit is part of their nature, an intrinsic property that can't be removed. Over time, this internal radiation damages the crystal structure itself, a process called metamictization. Highly radioactive crystals can become amorphous, losing their crystalline order entirely. Zircon, a common mineral, sometimes contains traces of uranium and shows varying degrees of structural damage. Despite this, most radioactive minerals in collections are safe when handled occasionally and stored. With reasonable precautions, they are tangible links to nuclear processes happening slowly within Earth. Each decay event, a tiny release of energy left over from the formation of elements in ancient stars. Crystal faces grow at different rates, creating varied shapes. A crystal's shape reflects which faces grew fastest and which grew slowest. Fast-growing faces become small or disappear because they grow themselves out of existence, while slow-growing faces dominate the final form. This is why quartz crystals often show large prism faces and smaller pyramid faces. The prism faces grow slowly, remaining prominent, while other potential faces grow so fast they shrink away. The relative growth rates depend on the atomic structure of each face, how easily atoms attach, and environmental conditions. By altering temperature or adding impurities, crystal growers can influence which faces develop. This principle is used in industrial crystal growth to create desired shapes. In nature, the same principle produces endless variety. Pyrite, iron sulfide, can form cubes, octahedrons, or pyritohedrons, depending on conditions. Calcite appears in over 300 different forms, each one a variation on the same underlying structure. Understanding growth rates helps mineralogists predict crystal shapes and gem cutters decide how to orient their cuts. It reveals that the external form of a crystal is not just geometry but a record of its growth history. Each face a page in the story of its creation. Crystals can contain other minerals as inclusions. Sometimes during growth, a crystal engulfs foreign material, trapping it inside. These inclusions can be other minerals, gas bubbles, liquid droplets, or even organic material. Quartz is particularly known for its inclusions. Rutilated quartz contains golden needles of rutile, titanium oxide, crisscrossing the interior like tiny hairs. Tourmalinated quartz holds black tourmaline crystals, frozen in clear quartz. Some quartz contains liquid and gas inclusions, ancient water and air, trapped millions of years ago. These are called fluid inclusions, and they provide valuable information about the conditions under which the crystal formed. By studying the temperature at which the trapped liquid and gas phases homogenize, scientists can estimate the formation temperature. Inclusions can enhance a crystal's beauty or diminish it, depending on perspective. Jewelers often prefer clean stones, but collectors prize included specimens for their uniqueness. A quartz with a landscape of included minerals resembles a snow globe or diorama. Each inclusion tells a story of what was present during growth. A snapshot of the environment preserved forever in crystal. Some inclusions create stunning visual effects in gemstones. Certain inclusions align in ways that produce remarkable optical effects. Star sapphires and star rubies owe their stars to tiny needles of rutile oriented along the crystal's internal axes. When the stone is cut as a cabochon, a domed shape, light reflects off these needles, creating a glowing star that seems to float on the surface. This is called asterism. Cat's eye stones like chrysoberyl show chatoyancy, a band of light that moves across the surface as the stone is tilted. This effect comes from parallel fibers or tube-like inclusions that reflect light like a cat's slit pupil. Labradorite displays labradorescence, flashes of blue, green, and gold caused by light scattering from thin layers within the crystal. These optical effects turn inclusions from flaws into features, adding value and wonder. They remind us that imperfection can create beauty, that the unplanned and accidental sometimes produce effects more striking than any human design. In the world of crystals, what is trapped inside can be as important as the crystal itself, shaping appearance and value in unexpected ways. Crystals form the foundation of all rocks on Earth. The ground beneath your feet is made of crystals, countless tiny grains interlocking to form solid rock. Granite is a mosaic of quartz, feldspar, and mica crystals. Sandstone is made of rounded quartz grains cemented together. Limestone is composed of calcite crystals, sometimes the shells of ancient sea creatures. Even volcanic glass like obsidian, though not crystalline itself, forms from melted crystals. Nearly every rock is either made of crystals or derived from them. This means the entire crust of Earth is essentially a vast crystal structure, layers upon layers of mineral grains fitted together. Mountains are sculptures of interlocking crystals worn by wind and water. Beaches are fragments of broken crystals, tumbled smooth. The sand between your toes is mostly quartz, each grain a tiny crystal, survivor of erosion. Understanding this transforms our view of the landscape. What seems solid and monolithic is actually granular, a collection of individuals held together. The Earth itself is built from crystals, from the microscopic to the massive, from the common to the rare, all contributing to the structure of the planet we walk upon. Certain crystals can conduct electricity better than others. Most crystals are insulators, blocking the flow of electric current, but some have properties that make them conductors or semiconductors. Graphite, a form of carbon, conducts electricity because its layered structure allows electrons to move freely between planes. Metallic minerals, like native copper or silver, also conduct well. Silicon, the basis of modern electronics, is a semiconductor, conducting under certain conditions. When doped with impurities, silicon crystals become transistors, the building blocks of computers and phones. Every electronic device relies on the controlled properties of crystalline silicon. Other crystals exhibit piezoelectricity, generating a voltage when squeezed or vibrating when voltage is applied. Quartz is strongly piezoelectric, which is why it's used in watches and oscillators. Applying an alternating current makes quartz vibrate at a precise frequency, creating a reliable timekeeping signal. Tourmaline and topaz also show piezoelectric properties. This connection between mechanical stress and electricity emerges from the crystal's asymmetric structure. Pressure distorts the lattice, shifting charged atoms and creating a voltage. Releasing the pressure reverses the effect. This interplay of structure and property makes crystals essential to technology, silent partners in nearly every modern device. Quartz is one of the most common minerals on Earth. If you pick up a random pebble, there's a good chance it contains quartz. This mineral, silicon dioxide, makes up about 12% of Earth's continental crust. It forms in a huge range of environments, from cooling magma to sedimentary deposits to metamorphic, rocks. Its chemical simplicity, just silicon and oxygen, means it forms easily. Its hardness, 7 on the Mohs scale, means it resists weathering and erosion. While softer minerals break down, quartz persists, accumulating in sands and soils. Most beach sand is quartz, billions of tiny crystals, worn smooth by waves. Quartz comes in many varieties, each with its own name. Clear quartz is rock crystal, purple is amethyst, pink is rose quartz, yellow is citrine, smoky gray is smoky quartz. Banded varieties are agate and jasper. Despite this diversity, all are the same mineral, with the same crystal structure. Quartz is also remarkably pure, often forming without significant impurities. This purity makes it useful. Pure quartz can be melted and drawn into optical fibers for telecommunications. Crushed quartz is used in concrete and glass. Silicon for electronics comes from quartz. This humble, common mineral is foundational to both geology and technology. Amethyst owes its purple color to iron and natural radiation. The rich purple of amethyst has captivated humans for millennia. This variety of quartz begins as colorless silicon dioxide, but trace amounts of iron replace some silicon atoms in the lattice. When natural radiation from surrounding rocks strikes these iron centers, it alters their electron structure, causing them to absorb certain wavelengths of light. The result is purple, ranging from pale lilac to deep violet. The intensity depends on iron concentration and radiation exposure. Some amethyst shows color banding, stripes of darker and lighter purple, reflecting variations in growth conditions. Heat can alter amethyst, turning it yellow to create citrine, a change that occurs naturally in some deposits and is replicated by gem dealers. Amethyst forms in geodes, hollow rocks where crystals grow inward from the walls. These geodes can range from fist-sized to large enough to walk inside. When split open, they reveal glittering purple caverns, each crystal a 6-sided prism tipped with pyramids. The ancient Greeks believed amethyst prevented intoxication, naming it after the Greek words for not and drunken. While this property is mythical, the beauty remains real, a gift of iron, radiation, and time. Rose quartz gets its pink color from microscopic mineral fibers. Unlike most colored quartz varieties, rose quartz rarely forms distinct crystals. Instead, it grows as massive formations, large chunks with no crystal faces. Its soft pink color, ranging from pale blush to deeper rose, comes from microscopic fibers of dumortierite or other minerals aligned throughout the quartz. These fibers scatter light, creating the translucent, milky appearance characteristic of rose quartz. The color can fade with prolonged exposure to light, as the radiation-damaged centers responsible for pink slowly heal. Most rose quartz comes from pegmatites, those very coarse-grained igneous rocks where crystals grow exceptionally large. Occasionally, rare, well-formed rose quartz crystals are found, and these are highly prized by collectors. Rose quartz has a gentle, calming appearance, which has made it popular for carvings and decorative objects. Its soft color and smooth texture when polished give it a soothing quality. Unlike the brilliant faceted gems, rose quartz invites touch, its warmth and gentle hue creating a sense of quiet beauty. It asks for no spotlight, content to glow softly, a whisper rather than a shout. Smoky quartz darkens from exposure to natural radiation over time. Smoky quartz ranges from pale gray to nearly black, a coloration caused by natural radiation affecting the crystal structure. The silicon dioxide lattice contains aluminum impurities, and when radiation from surrounding radioactive minerals strikes the crystal over millions of years, it creates color centers that absorb light. The silicon dioxide lattice, longer the exposure, the darker the crystal becomes. Some smoky quartz is so dark it appears black, called Morian. Despite its dark appearance, smoky quartz remains transparent, and light passing through reveals its true color. The effect can be replicated artificially by irradiating clear quartz, a practice sometimes used in the gem trade. Natural smoky quartz often forms in granite pegmatites, where radioactive elements like uranium are present. The Alps are famous for producing exceptional smoky quartz crystals, some several feet long. Locals called them mountain crystals, considering them solidified ice that would never melt. The dark color gives smoky quartz a mysterious quality, as though it holds shadows within. Yet it remains quartz, sharing the same structure as its clear cousin, proof that color is only skin deep, a response to environment rather than essence. Citrine is rare in nature, but common in markets. Natural citrine, yellow to orange quartz, is uncommon in nature. Most citrine sold today began life as amethyst or smoky quartz and was heat-treated to change color. Heating amethyst to several hundred degrees alters the iron centers responsible for purple turning them yellow or orange. The result is indistinguishable from natural citrine without advanced testing. True natural citrine forms in specific conditions where the iron impurities and oxidation states are just right, often in locations like Brazil or Madagascar. It tends to be paler than heat-treated material, a subtle lemon yellow rather than deep orange. The name comes from citrus, reflecting its color. Citrine has been used in jewelry for thousands of years, prized for its warm, sunny hue. It doesn't fade in light like amethyst can, making it a durable choice. The abundance of affordable citrine in the market is a testament to human ingenuity in transforming one beautiful thing into another. While purists may prefer natural citrine, heat-treated stones are still quartz, their crystal structure unchanged. The treatment simply unlocks a different aspect of the mineral's potential, revealing colors that might have emerged naturally under different circumstances. Diamonds are pure carbon, crystallized under extreme pressure, deep in Earth's mantle, more than 100 miles below the surface. Conditions are severe. Temperatures exceed 1,000 degrees, and pressures immense. Under these conditions, carbon atoms, the same element that forms graphite, arrange themselves differently. Instead of layers, they form a three-dimensional network, where each carbon bonds to 4 others in a tetrahedral pattern. This structure is diamond, the hardest natural material known. The strong bonds in all directions make diamond incredibly resistant to scratching and compression. Diamonds form in the mantle and remain there unless volcanic eruptions carry them upward in magma that rises quickly. These eruptions create kimberlite pipes, carrot-shaped formations that are the primary source of diamonds. The journey from mantle to surface is violent and fast, preventing diamonds from converting back to graphite. Most diamonds are over 1 billion years old, formed in the ancient past when the mantle was hotter and more active. Holding a diamond is holding ancient carbon, pressed and heated in Earth's depths, carried upward by volcanic fury, and somehow surviving the journey intact. Its brilliance and fire are just light interacting with its crystal structure, but the journey it represents is extraordinary. Not all diamonds are clear. Many show colors from impurities. While colorless diamonds are prized, colored diamonds are rare and valuable. Boron impurities create blue diamonds, the Hope diamond being the most famous. Nitrogen is more common, producing yellow or brown tints. Most diamonds contain some nitrogen, but in low concentrations it's barely noticeable. Higher concentrations deepen the color to canary yellow. Pink, red, and purple diamonds owe their color to structural distortions caused by pressure during formation. Green diamonds get color from exposure to natural radiation over millions of years. Black diamonds are colored by inclusions of graphite or other minerals. The most intense colors are called fancy diamonds, and some hues are rarer than others. Red diamonds are exceptionally rare, with only a handful of significant specimens known. Blue and pink are also highly valued. These colors add character, transforming carbon into a palette of possibilities. While colorless diamonds are celebrated for their purity, colored diamonds show how imperfection or stress can create uniqueness. They remind us that diamonds, like all crystals, are products of their environment, bearing the marks of the conditions that formed them. Graphite and diamond are both pure carbon in different forms. Carbon is an element of remarkable versatility. Arrange its atoms one way, and you get graphite, soft and slippery, used in pencils. Arrange them another way, and you get diamond, the hardest natural material. This difference arises entirely from structure. In graphite, carbon atoms bond strongly in flat sheets, but the sheets connect weakly, allowing them to slide past each other. This makes graphite an excellent lubricant and gives it its greasy feel. In diamond, every carbon atom bonds strongly to four neighbors in a three-dimensional network, locking everything rigidly in place. Same element, entirely different properties. Under normal surface conditions, graphite is more stable than diamond. Diamonds are actually metastable, meaning they should theoretically convert to graphite over time. Fortunately, this conversion is so slow at room temperature that diamonds persist indefinitely for human purposes. Under high pressure and temperature, the reverse can occur, graphite converting to diamond. This is how synthetic diamonds are made, by recreating mantle conditions in a laboratory. The existence of both graphite and diamond from the same element illustrates how structure determines properties, a fundamental principle of crystallography and chemistry. Rubies and sapphires are the same mineral with different colors. Corundum, aluminum oxide, is one of the hardest minerals, after diamond. Pure corundum is colorless, but trace impurities create the gemstones we cherish. Chromium turns corundum red, creating ruby. Iron and titanium together create blue sapphire. But sapphire isn't only blue. Corundum comes in nearly every color: orange, yellow, pink, green, and even colorless. And all except red are called sapphire. Padparadscha sapphires are prized for their salmon pink-orange hue. Star sapphires show asterism from oriented inclusions. Despite these variations, they are all corundum, aluminum oxide, with the same crystal structure and hardness. Ruby's name comes from Latin for red, while sapphire comes from Greek, originally referring to blue stones including lapis lazuli. Today, the names are standardized. Red corundum is ruby. All other colors are sapphire. Some specimens even show multiple colors in one crystal, called party sapphires. These gemstones have been treasured for millennia, appearing in crowns and religious artifacts. Their hardness, second only to diamond, makes them durable for jewelry. Their colors, vivid and varied, appeal to every taste. Whether glowing red or deep blue, all corundum crystals share the same fundamental nature. Their colors, mere accents on a common theme. Emeralds are colored by chromium and sometimes vanadium. Emerald is the green variety of beryl, a beryllium aluminum silicate. Pure beryl is colorless, but the addition of chromium or vanadium produces the vivid green that defines emerald. The color can range from yellowish green to deep, rich green, with the most prized stones showing a pure, saturated hue. Unlike diamonds, emeralds almost always contain inclusions, tiny fractures, mineral crystals, or fluid-filled cavities. These are so common that the industry calls them jardin, French for garden, as though the inclusions are part of the stone's natural beauty. Indeed, a flawless emerald is exceptionally rare and valuable. Most emeralds are treated with oils or resins to fill surface-reaching fractures, improving clarity and color. This treatment is widely accepted because emeralds have been treated this way for centuries. The finest emeralds come from Colombia, where conditions produce stones of exceptional color and transparency. Other sources include Zambia, Brazil, and Afghanistan. Emeralds have adorned royalty and religious icons for thousands of years. Incas and Aztecs mined them, and Cleopatra famously favored them. Their green is the green of spring and life, a color that never seems to fade or tire, eternally fresh and vibrant. Aquamarine is the blue variety of the same mineral as emerald. While emerald is the green version of beryl, aquamarine is the blue. Iron impurities give aquamarine its color, a pale to deep blue, sometimes with greenish tints. The name means seawater, reflecting its oceanic hues. Aquamarine tends to be cleaner than emerald, with fewer inclusions, allowing cutters to produce large, clear gemstones. The color is generally paler than sapphire, more delicate and soothing. Heat treatment can remove unwanted yellow or green tints, deepening the blue. This treatment is stable and widely accepted. Aquamarine crystals can grow quite large, sometimes weighing many pounds. These giants are typically cut into multiple gems or carved into ornamental objects. Brazil is a major source, producing aquamarine in a range of colors. The Santa Maria aquamarines, named after a Brazilian mine, are prized for their deep, saturated blue. Pakistan and Madagascar also produce fine material. Aquamarine has a calming quality, its color evoking clear water and open skies. Unlike the fiery brilliance of diamonds or the deep intensity of emeralds, aquamarine is gentle and serene, a stone that invites contemplation rather than demands attention. It is the whisper of the ocean, captured in crystalline form. Topaz comes in many colors, though blue is most popular today. Natural topaz is often colorless or pale blue, brown, or yellow. The vivid blue topaz seen in jewelry is almost always treated, irradiated, and heated to intensify color. This treatment is permanent and produces shades from pale sky blue to deep London blue. Topaz is aluminum silicate fluoride, and its crystal structure allows it to grow in large, well-formed crystals. It's relatively hard, 8 on the Mohs scale, making it durable for jewelry. Imperial topaz, a golden orange to pink variety, is rare and highly valued. Found primarily in Brazil, this color is natural and commands premium prices. Topaz has perfect cleavage, meaning it can split easily along certain planes, a consideration for cutters and wearers. Despite this, it's a popular gem due to its affordability and range of colors. Historically, many yellow stones were called topaz, leading to confusion. True topaz is specifically the mineral described above. The name may come from an island in the Red Sea, though the etymology is uncertain. Topaz crystals can grow quite large, with museum specimens weighing hundreds of pounds. For jewelry, smaller stones are cut and faceted, their brilliance and color making them attractive and accessible gems. Garnets are actually a group of related minerals, not just one. When people think of garnet, they often picture dark red stones. But garnet is not a single mineral, but a family of silicates with similar crystal structures. All garnets form in the cubic system, typically as dodecahedrons or trapezohedrons, 12 or 24-sided shapes. The most common is almandine, the dark red variety used in jewelry. Pyrope is also red, but lighter and brighter. Spessartine is orange. Andradite is yellow, green, or black. Grossula can be green, yellow, orange, or pink. And uvarovite is a rare emerald green. Some garnets even change color under different lighting, appearing blue-green in daylight and purple-red under incandescent light. This color change rivals that of alexandrite. Garnets form in metamorphic rocks, where heat and pressure rearrange minerals into new forms. They are also found in certain igneous rocks. Because they resist weathering, garnets accumulate in sediments and can be found in river sands. Prospectors sometimes use garnets as indicator minerals, suggesting the presence of diamond-bearing kimberlites. Garnets have been used since ancient times, found in Egyptian, Roman, and medieval jewelry. Their name may come from Latin for seed, referring to their resemblance to pomegranate seeds. This diverse family shows how a common crystal structure can produce a spectrum of compositions and colors. Pearls are not crystals, but are made by living organisms. Unlike gemstones formed in rock, pearls are biological creations. When an irritant, a grain of sand or parasite, enters an oyster or mussel, the animal responds by coating it with nacre, layers of calcium carbonate, and protein. Over months or years, layer upon layer build up, forming a pearl. The nacre is composed of tiny aragonite crystals arranged in overlapping plates, creating a smooth, lustrous surface. This structure diffracts light, giving pearls their iridescent glow. Natural pearls are rare, formed by chance in wild mollusks. Most pearls today are cultured, produced by intentionally introducing an irritant into oysters and harvesting the results after several years. Freshwater pearls come from mussels, while saltwater pearls come from oysters. Colors range from white to cream, pink, gold, and even black, depending on the species and water conditions. Unlike faceted gems, pearls need no cutting or polishing. They emerge from the shell, ready to wear. Their luster and shape, ideally round, determine value. Pearls have been treasured for thousands of years, symbols of purity and elegance. Though not crystalline in the strict sense, they are mineralogical wonders, proof that life and minerals can collaborate to create beauty. Opals contain water and diffract light into rainbow colors. Opal is unlike most gemstones. It is not a crystal, but an amorphous solid, a hardened gel of silica and water. Precious opal contains microscopic silica spheres arranged in a regular pattern. Light passing through this structure diffracts, splitting into spectral colors. The play of color, flashes of red, green, blue, and yellow, depends on sphere size and arrangement. Larger spheres produce reds and oranges. Smaller ones produce blues and greens. The background color can be white, black, or crystal, and each type has its own name. Black opal, with dark body color, shows the most vivid play of color. Fire opal is transparent orange to red, prized even without color play. Boulder opal includes the host rock, creating unique patterns. Opals form in sedimentary environments, where silica-rich water fills cracks and voids, slowly hardening over time. Australia produces most of the world's precious opal, though significant deposits exist in Ethiopia, Mexico, and other locations. Opals are softer than most gems, around 5.5 on the Mohs scale, and contain water. making them vulnerable to drying and cracking. They require careful handling. Yet their unique beauty, the dance of colors within, makes them endlessly fascinating. No two opals are alike, each one a frozen firework, a spectrum captured in stone. Jade refers to two different minerals, jadeite and nephrite. Jade has been revered for thousands of years, especially in China and Mesoamerica. Yet jade is not a single mineral but two distinct ones with similar appearance. Jadeite is a pyroxene, sodium, aluminum, silicate, and is rarer and generally more valuable. Nephrite is an amphibole, calcium, magnesium, silicate, and is more common. Both are tough due to their interlocking fibrous crystal structure, making them ideal for carving. This toughness is different from hardness. Jade is not particularly hard, around 6 to 7 on the Mohs scale, but its fibrous nature makes it resistant to breaking. You can carve it without it shattering. Colors range from white to deep green, with lavender, yellow, and black also occurring. The most prized jadeite is imperial jade, a vivid emerald green. Nephrite tends toward darker, more muted greens and creamy whites. Chinese culture has valued jade for millennia, considering it more precious than gold, a symbol of virtue and immortality. In Mesoamerica, the Olmec, Maya, and Aztec cultures carved jade into masks, jewelry, and ceremonial objects. The two minerals were not distinguished until modern times, both called jade in recognition of their shared qualities, beauty, toughness, and cultural significance. Turquoise is a copper aluminum phosphate treasured for millennia. Turquoise is one of the oldest known gemstones, used by ancient Egyptians, Persians, and Native Americans. Its distinctive blue to green color comes from copper, with greener stones containing more iron. The color can be uniform or veined with matrix, the host rock, creating intricate patterns. Turquoise forms in arid regions, where copper-bearing water percolates through aluminum-rich rock, depositing the mineral in veins and nodules. It is relatively soft, 5 to 6 on the Mohs scale, and porous, meaning it can absorb oils and change color over time. Much turquoise is stabilized, treated with resins to harden it and prevent color change. The finest turquoise comes from Iran, known historically as Persian turquoise, prized for its intense, pure blue. The American Southwest produces significant turquoise, especially from Arizona and Nevada, often with distinctive matrix patterns. Native American jewelry and art have made Southwestern turquoise famous worldwide. Turquoise has been used in inlay, carvings, beads, and cabochons for thousands of years. Its sky blue color is calming and evocative, symbolizing protection and good fortune in many cultures. Though not as hard or brilliant as other gems, turquoise has a warmth and character that few stones can match, a connection to earth and sky, desert and water. Lapis lazuli is actually a rock made of several minerals. Lapis lazuli is not a single mineral, but a rock composed primarily of lazurite, a blue feldspathoid, along with calcite, pyrite, and other minerals. The deep blue comes from lazurite, while white streaks are calcite, and golden flecks are pyrite. The combination creates a stone that resembles a starry night sky. Lapis has been prized since ancient times, mined in Afghanistan for over 6,000 years, and traded across the ancient Egyptians used it in jewelry and ground it to make blue eyeshadow. During the Renaissance, artists ground lapis into ultramarine pigment, the finest blue available, more valuable than gold. Its use in paintings gave the Virgin Mary's robes their iconic deep blue. Lapis is relatively soft, 5 to 6 on the Mohs scale. but takes a good polish. It is typically cut as cabochons or carved into beads, cameos, and ornamental objects. The finest lapis is a deep, even blue, with minimal calcite and attractive pyrite. Lower grades show more white or are paler, despite being a rock rather than a single crystal. Lapis lazuli has earned its place among treasured gemstones, valued for its rich color and historical significance. It connects us to ancient civilizations, to artists and royalty, to a time when blue was rare and precious. Fluorite displays vivid colors and perfect octahedral cleavage. Fluorite, calcium fluoride, is a collector's favorite, known for its stunning colors and crystal forms. It occurs in purple, green, blue, yellow, pink, and colorless varieties, sometimes with multiple colors in one crystal. Color banding creates attractive patterns. Fluorite is not hard, only 4 on the Mohs scale, which limits its use in jewelry, but makes it easy to carve and shape. Its defining characteristic is perfect octahedral cleavage, meaning it splits cleanly along 4 directions, forming 8-sided shapes. A light tap can cleave fluorite into perfect octahedrons. This cleavage reflects its cubic crystal structure. Fluorite often forms as cubes or octahedrons, with smooth, glossy faces. It also shows strong fluorescence under UV light, glowing blue, green, or other colors. The term fluorescence is derived from fluorite. Fluorite forms in hydrothermal veins and is often associated with lead and zinc ores. China, Mexico, and the United States produce notable specimens. Blue John, a banded purple and yellow fluorite from England, has been carved into vases and ornaments for centuries. Beyond aesthetics, fluorite is industrially important, used in steelmaking, as a flux in smelting, and in producing hydrofluoric acid. This colorful, cleaving mineral is both beautiful and useful. Calcite makes up most of limestone and marble. Calcite, calcium carbonate, is one of Earth's most common minerals. It forms the bulk of limestone, a sedimentary rock created from accumulated shells and skeletons of marine organisms. Over millions of years, these remains settle on ocean floors, compact and lithify into rock. When limestone undergoes metamorphism, heat and pressure recrystallize the calcite into marble, where individual calcite crystals grow larger and interlock. Calcite also forms in caves as stalactites and stalagmites, deposited by dripping mineral-rich water. It occurs in a bewildering variety of crystal forms, over 300 documented, from simple rhombs to complex scalenohedrons. Clear, calcite crystals, called Iceland spar, exhibit strong double refraction. Look through one, and you see 2 images of everything. This optical property results from calcite's crystal structure and was historically important in understanding light. Calcite reacts vigorously with acid, fizzing as carbon dioxide is released, a simple test used by geologists to identify it. Its abundance and versatility make calcite fundamental to understanding Earth's geology, from ocean organisms to mountain marble, from cave decorations to optical curiosities. Calcite is everywhere, quietly shaping the planet. Gypsum forms when seawater evaporates, leaving crystals behind. Gypsum, calcium sulfate with water, is an evaporite mineral, meaning it precipitates when water evaporates. In ancient times, shallow seas and salt lakes dried under the sun, leaving layers of gypsum and other salts. Today, gypsum forms in similar environments, including desert playas and coastal lagoons. It is soft, only 2 on the Mohs scale, easily scratched by a fingernail. This softness made it useful historically for carving and as a building material. Alabaster, a fine-grained gypsum, was carved into statues and vessels. Selenite is transparent crystalline gypsum, forming flat, blade-like crystals or fibrous satin spar with a silky luster. Desert roses are rosette-shaped gypsum formations that include sand grains, forming in arid regions. The giant selenite crystals in Mexico's Cave of Crystals are the most spectacular examples, some over 30 feet long. Gypsum is also industrially important, ground into plaster for walls and ceilings, the plaster of Paris. When heated, gypsum loses water and can be mixed with water again to harden, making it ideal for construction. This humble mineral, soft and common, has shaped human civilization from ancient sculptures to modern homes. Halite is rock salt, sodium chloride in crystal form. Halite is the mineral form of table salt, sodium chloride. It forms in evaporating bodies of water, just like gypsum, crystallizing when seawater or salt lake water becomes saturated. Ancient seas left vast salt deposits underground, mined today for salt. Halite crystals are cubic, forming perfect little cubes with smooth faces. They have perfect cubic cleavage, breaking into smaller cubes when struck. Pure halite is colorless, but impurities can tint it pink, blue, or yellow. Himalayan pink salt owes its color to trace minerals. Halite is soft, 2.5 on the Mohs scale, and tastes salty, a definitive test. It dissolves easily in water, so halite doesn't survive in wet climates unless protected underground. Salt domes, massive underground. Columns of halite rise through overlying rock due to their lower density, creating traps for oil and gas. These domes have been important in petroleum geology. Salt has been economically vital throughout history, essential for preserving food and as a currency in some cultures. The word salary comes from salt. Despite its simplicity, halite has profoundly influenced human society, from ancient trade routes to modern industry. Every grain of table salt is a tiny cube, a crystal that preserves food and life itself. Mica splits into thin, flexible sheets due to its structure. Mica is a group of silicate minerals with a distinctive layered structure. The most common are muscovite, colorless to pale, and biotite, dark brown to black. Mica's atoms bond strongly within sheets, but weakly between sheets, allowing it to cleave into thin, flexible, transparent layers. These sheets can be peeled off like pages in a book. Historically, mica was used as window panes, called isinglass, because it was heat-resistant and transparent. Today, mica is used in electronics as an insulator, in cosmetics for shimmer, and in various industrial applications. Large mica crystals form in pegmatites, those coarse-grained igneous rocks where minerals grow big. Muscovite sheets, several feet across, have been mined. Mica crystals are typically flat, hexagonal in outline, reflecting their crystal system. When light hits mica, it reflects from multiple internal layers, creating a pearly luster. Ground mica adds sparkle to paints and cosmetics. Though not a gemstone, mica's unique properties make it valuable. Its cleavage is so perfect and its sheets so flexible that it seems more organic than mineral, almost like a natural film or foil, a bridge between the rigid and the pliant. Pyrite is often called fool's gold for its metallic yellow luster. Pyrite, iron sulfide, has deceived many prospectors with its golden glint. Its name comes from the Greek word for fire, because striking pyrite against metal produces sparks. Pyrite forms in many environments, from sedimentary rocks to hydrothermal veins. It often crystallizes as perfect cubes or pyritohedrons, 12-sided shapes with pentagonal faces. Clusters of intergrown pyrite crystals can be stunningly geometric. Its metallic luster and pale brassy yellow color resemble gold, but pyrite is brittle and hard, 5 to 6 on the Mohs scale. Whereas gold is soft and malleable, pyrite is also much lighter than gold. Despite its nickname, pyrite is valuable in its own right, historically used to produce sulfur and sulfuric acid. Today, it's mined for sulfur in some locations. Pyrite can alter to iron oxides, creating gossans, rusty outcrops that prospectors use to locate deeper ore deposits. Marcasite is a polymorph of pyrite, same chemistry but different crystal structure, and it occurs in sedimentary rocks. Pyrite's abundance and distinctive appearance make it a favorite among collectors. Its geometric perfection and metallic shine are striking. Though not gold, pyrite has its own allure, a glittering reminder that not all that glitters is gold, yet everything that glitters has its own worth. Hematite is an iron oxide that can be metallic or earthy. Hematite iron oxide is one of the most important iron ores. It occurs in two main forms, metallic and earthy. Specular hematite forms shiny, metallic crystals or masses with a steel-gray color. When polished, it looks like a mirror. Earthy hematite, often called red ochre, is dull and powdery, staining fingers red. When scratched, all hematite leaves a red streak, a diagnostic property. This red comes from oxidized iron, rust in its natural form. Hematite forms in diverse environments, from sedimentary iron formations billions of years old to weathering zones where iron minerals oxidize. Ancient Precambrian banded iron formations, layers of hematite and chert, are the primary source of iron ore worldwide. These formed when early oceans, rich in dissolved iron, encountered oxygen produced by photosynthetic bacteria. Iron oxidized and precipitated, creating vast deposits. Hematite has been used as a pigment since prehistoric times, appearing in cave paintings and later in pottery and art. The red ochre found at archaeological sites is hematite. Its name comes from the Greek word for blood, reflecting its color. Heavy and magnetic when heated, hematite is both beautiful and industrially essential, a mineral that helped build the modern world. Magnetite is a naturally magnetic iron oxide. Magnetite is iron oxide, like hematite, but with a different structure and properties. Its most striking feature is natural magnetism. Some magnetite specimens, called lodestones, are magnetic enough to attract iron objects. Ancient navigators used lodestones as primitive compasses, the first magnetic tools. Magnetite is black and opaque with a metallic luster. It is strongly magnetic, distinguishing it from similar minerals. When finely powdered, magnetite is an important iron ore. It forms in igneous and metamorphic rocks and is common in black sand on beaches, concentrated by wave action because of its high density. Magnetite crystallizes in the cubic system, often forming octahedrons. Some crystals show striations, fine grooves on their faces. Magnetite's magnetism arises from the alignment of electron spins in its crystal structure, creating magnetic domains. This makes it one of the few minerals detectable with a magnet. Magnetite has been crucial in understanding Earth's magnetic field. Ancient magnetite crystals record the orientation of the field when they formed, revealing that Earth's poles have reversed many times. This paleomagnetism is key evidence for plate tectonics. Magnetite connects us to Earth's hidden magnetic forces, a mineral that literally points the way. Malachite's green bands form from weathering copper deposits. Malachite, a copper carbonate hydroxide, is unmistakable with its vivid green color and distinctive banding. It forms in the oxidation zones of copper deposits, where weathering copper minerals react with carbonate-rich water. Malachite precipitates as tiny crystals that grow in radiating clusters, creating botryoidal grape-like surfaces. Cutting and polishing reveal concentric bands of lighter and darker green, creating intricate patterns. No two pieces are alike. Malachite is relatively soft, 3.5 to 4 on the Mohs scale, but takes a good polish. It has been used as an ornamental stone for thousands of years, carved into jewelry, vases, and inlaid in furniture. The Russian Tsars favored malachite, decorating palace rooms with it. As a pigment, ground malachite provided a rich green color used in ancient Egyptian art and later in European painting. Its toxicity, due to copper content, means handling it as pigment requires care. Malachite often occurs with azurite, a blue copper carbonate, creating striking green and blue combinations. The color contrast is dramatic and beautiful. Malachite's green is the green of oxidation, the color of copper exposed to air and water, a mineral signature of transformation. Azurite's deep blue complements malachite in copper deposits. Azurite is another copper carbonate, closely related to malachite but blue instead of green. It forms under similar conditions in the weathering zones of copper deposits. Azurite's deep azure blue is striking, one of the richest blues in the mineral world. Like malachite, azurite often forms botryoidal masses and small prismatic crystals. It is also soft, around 3.5 to 4 on the Mohs scale, limiting its use in jewelry, but making it suitable for carving. Azurite was historically ground into blue pigment, used in illuminated manuscripts and paintings. However, azurite can alter to malachite over time, sometimes causing paintings to turn greenish as the blue mineral transforms. This instability reduced its use in favor of more stable blues like ultramarine. Azurite and malachite frequently occur together, creating blue and green banded stones called azurmalachite, prized for their color contrast. Azurite crystals can be darker than any sky, an intense midnight blue that seems to hold depth. Its color is pure and saturated, a blue that feels almost liquid. Azurite, like malachite, is a copper mineral, but where malachite signals green growth, azurite is the blue of depth and mystery, a complementary contrast written in stone. Sulfur forms bright yellow crystals near volcanoes. Sulfur, the element, can occur as a mineral in its native form. Around volcanic vents and hot springs, sulfur sublimates from gases and recrystallizes as bright yellow crystals. These crystals are soft, only 1.5 to 2.5 on the Mohs scale, and have a resinous luster. Pure sulfur is a brilliant lemon yellow, unmistakable. It forms orthorhombic crystals, often as dipyramids, double pyramids joined at the base. Sulfur burns easily, producing sulfur dioxide gas with a sharp, acrid smell. This combustibility made sulfur useful historically in making gunpowder and matches. Today, sulfur is essential in producing sulfuric acid, one of the most important industrial chemicals. Large sulfur deposits also form in evaporite environments and from bacterial action on gypsum. Sulfur's bright color and association with volcanic activity give it a fiery, almost dangerous character. Standing near a fumarole, surrounded by yellow sulfur crystals, the smell of sulfur dioxide feels otherworldly, a landscape more chemical than earthly. Yet sulfur is essential to life, a component of amino acids and proteins. This vivid yellow mineral connects fire and life, destruction and creation, in crystalline form. Corundum is the second hardest natural mineral after diamond. Corundum, aluminum oxide, ranks 9 on the Mohs hardness scale, just below diamond's 10. This exceptional hardness makes it valuable both as a gemstone and as an abrasive. Industrial corundum, often called emery, is crushed and used in sandpaper, grinding wheels, and polishing compounds. Corundum forms in aluminum-rich, silica-poor environments, typically in metamorphic rocks, or as a primary mineral in certain igneous rocks. Its crystal structure is tightly packed, explaining its hardness. Pure corundum is colorless, but trace elements create the colors we treasure: ruby and sapphire. Corundum crystals often form as hexagonal prisms or barrel shapes. They can grow quite large, with some crystals weighing many pounds. Corundum's hardness and inertness mean it resists weathering and accumulates in placer deposits, gravels, where heavy minerals concentrate. Historically, these places were the primary source of rubies and sapphires. Today, many are mined directly from host rock. Corundum's combination of beauty, hardness, and rarity makes it one of the most prized gemstones. Its durability means it lasts forever in jewelry, a stone that can be passed down through generations without wearing away. Beryl crystals can grow exceptionally large in pegmatites. Beryl, a beryllium aluminum silicate, forms some of the largest and most spectacular crystals known. In pegmatites, where slow cooling and abundant material allow extended growth, beryl can reach enormous sizes. Crystals weighing several tons have been found, some over 30 feet long, though most are not gem quality. Beryl forms hexagonal prisms, often with flat terminations. The crystal faces are typically smooth and striated. Pure beryl is colorless, but trace elements produce the famous gem varieties: emerald, aquamarine, morganite, heliodor, and others. Beryl is moderately hard, 7.5 to 8 on the Mohs scale, and generally durable. Its clarity and color make it a favorite for faceting. The name beryl comes from the Greek word for green, though not all beryls are green. Beryl is also the primary ore of beryllium, a light metal used in aerospace and electronics. Extracting beryllium from beryl requires care due to beryllium's toxicity. Despite this, beryl remains essential both for its beauty and its industrial importance. The largest beryl crystals, though not transparent, are geological marvels, evidence of Earth's capacity for creation on a grand scale. Tourmaline shows more color variety than almost any other mineral. Tourmaline is a complex boron silicate with a dizzying array of colors. It can be pink, red, green, blue, yellow, brown, black, or colorless, and often shows multiple colors in a single crystal. Watermelon tourmaline has a pink core and green rim, resembling its namesake. Party-colored tourmaline displays distinct color zones. This variety arises from changing chemical conditions during growth as different elements replace each other in the structure. Tourmaline is also strongly pleochroic, showing different colors when viewed from different angles. It forms in pegmatites and metamorphic rocks, often as long, slender prisms with vertical striations. Tourmaline is hard, 7 to 7.5 on the Mohs scale, and durable. It has been used as a gemstone for centuries, though often confused with other stones, until modern mineralogy distinguished it. Tourmaline is also pyroelectric and piezoelectric, generating electricity when heated or compressed. This property made it useful in pressure gauges, and other instruments. The name tourmaline comes from Sinhalese, referring to mixed-colored stones from Sri Lanka. No other mineral offers such a spectrum of colors in a single species, making tourmaline a favorite among collectors and jewelers alike. Peridot is the gem variety of olivine from deep in the mantle. Peridot is the yellowish-green gem form of olivine, a magnesium-iron silicate. Olivine is one of the first minerals to crystallize from cooling magma and is abundant in Earth's mantle. Most olivine is not gem quality, but occasionally transparent, well-colored. Crystals form in volcanic rocks or brought to the surface by volcanic activity. Peridot's color comes from iron, and it ranges from yellow-green to olive to brownish-green. Unlike many gems colored by trace impurities, peridot's color is part of its essential composition. It is found in basaltic lava flows, particularly in Hawaii, and in peridotite, a mantle rock, sometimes exposed by tectonics. Egypt's Zabargad Island was a famous ancient source. Meteorites also contain olivine, connecting peridot to extraterrestrial geology. Peridot is moderately hard, 6.5 to 7 on the Mohs scale, but can be brittle. It has high double refraction, meaning looking through it shows doubled images of inclusions. Peridot has a warm, glowing quality, a green that seems lit from within. It is the birthstone for August and has been treasured since antiquity. Ancient Egyptians mined it and called it the gem of the sun. Spinel was often confused with ruby until modern times. Spinel, magnesium aluminum oxide, occurs in a range of colors, but red spinel closely resembles ruby. For centuries, the two were not distinguished. Some of the most famous rubies in history, including the Black Prince's ruby in the British crown jewels, are actually spinels. Spinel forms in metamorphic rocks and crystallizes in the cubic system, often as octahedrons. Its hardness, 8 on the Mohs scale, is nearly equal to corundum, and its luster and brilliance rival ruby and sapphire. Spinel has no cleavage, making it durable. Colors include red, pink, orange, purple, blue, and black. The finest red spinels can match or exceed ruby in beauty and value. Spinel's confusion with ruby persisted until the 18th century, when chemistry and crystallography distinguished them. Today, spinel is recognized in its own right, appreciated for its color, brilliance, and durability. It's less well known than ruby or sapphire, making fine spinels undervalued compared to their beauty. Spinel also fluoresces under UV light, often glowing bright red, adding another dimension to its character. This underappreciated gem deserves recognition, a stone that has adorned crowns and confused gemologists, finally claiming its own identity. Zircon is one of the oldest minerals recording Earth's early history. Zirconium silicate, is extraordinary for its age. Some zircon crystals are over 4 billion years old, nearly as old as Earth itself. These ancient grains survive because zircon is extremely hard, 7.5 on the Mohs scale, and chemically resistant. Zircon forms in igneous rocks and persists through weathering, erosion, and even metamorphism, accumulating in sediments. When sediments are metamorphosed or melted, zircons often survive, carrying their age with them. Scientists use uranium-lead dating on zircons to determine the age of rocks. The oldest known zircon, from Australia, dates to 4.4 billion years, providing evidence that Earth had a solid crust and possibly water very early in its history. Zircon also occurs as a gemstone, with colors including colorless, yellow, brown, red, and blue. Heat treatment can enhance color turning brown zircon into blue or colorless. Zircon has high refractive index and dispersion, giving it brilliance, and fire similar to diamond. Unfortunately, it's often confused with cubic zirconia, a synthetic diamond simulant. Natural zircon deserves recognition, both as a gem and as a scientific treasure, a mineral that remembers Earth's infancy. Agate is banded chalcedony, formed in volcanic rock cavities. Agate is a variety of chalcedony, microcrystalline quartz, characterized by colorful banding. It forms in cavities in volcanic rock, where silica-rich water deposits layers over time. Each layer may be a slightly different color due to varying impurities, creating concentric bands. Agate can be translucent, and when cut and polished, the bands create beautiful patterns. Colors range from white and gray to red, brown, yellow, and black. Some agates show moss-like inclusions of manganese or iron, called moss agate. Others have eye-like circles, called eye agate. Agate is hard, 7 on the Mohs scale, and takes a high polish, making it popular for carvings, beads, and ornamental objects. Agate has been used since antiquity for seals, amulets, and jewelry. Each piece is unique, the banding never repeating. Large agate nodules can be sliced into many pieces, each slice showing the bid pattern. Geodes lined with agate are prized by collectors. The formation process is slow, layer upon layer, each one recording a moment in time. Agate is a stone of patience and accumulation, beauty built incrementally, proof that gradual processes can produce intricate artistry. Jasper is opaque, chalcedony, often with patterns and landscapes. Jasper is another variety of chalcedony, but unlike agate, it is opaque. It comes in a stunning array of colors and patterns, often with inclusions that create landscape-like scenes. Red jasper owes its color to iron oxide. Yellow jasper contains limonite. Some jasper, called picture jasper, shows patterns resembling landscapes, complete with skies, deserts, and mountains, all formed by mineral deposition. Orbicular jasper displays circular patterns. Dalmatian jasper is white, with black spots. Jasper has been used since prehistoric times, for tools, carvings, and jewelry. Its toughness, 7 on the Mohs scale, and ease of working made it ideal for early humans. Jasper artifacts have been found at archaeological sites worldwide. In ancient civilizations, jasper was carved into seals and amulets. Its earthy colors and patterns give it a grounded, natural feel, less flashy than faceted gems but rich in character. Polished jasper reveals depths and subtleties, colors blending and shifting. It is a stone that invites close examination, each piece telling a story in mineral pigments, landscapes frozen in silica, Earth's artistry, made tangible. Obsidian is volcanic glass, not a true crystal. Obsidian forms when lava cools so quickly that atoms don't have time to arrange into crystals. Instead, it solidifies as glass, an amorphous solid. Obsidian is typically black, but can also be brown, green, or even rainbow-sheened. Its fracture is conchoidal, breaking in smooth curves with sharp edges. This property made obsidian valuable to prehistoric peoples, who shaped it into blades, arrowheads, and tools. Obsidian tools are sharper than steel scalpels, and some surgeons still use obsidian blades. Obsidian forms in volcanic regions, especially where lava is rich in silica. Over time, obsidian can devitrify, slowly crystallizing into other minerals, so very old obsidian is rare. Obsidian's glassy luster and deep color give it a mysterious quality. Some varieties show sheen or iridescence, like rainbow obsidian, caused by thin layers within the glass. Snowflake obsidian contains white cristobalite crystals, creating a contrast. Though not crystalline, obsidian is a bridge between molten rock and solid mineral, a frozen moment of volcanic violence, glassy and smooth, sharp and beautiful. Ancient civilizations treasured crystals for adornment and power. Throughout history, humans have been drawn to crystals. Ancient Egyptians adorned themselves with lapis lazuli, turquoise, and carnelian. They placed crystals in tombs, believing they held protective powers for the afterlife. Mesopotamians carved cylinder, seals from stones like agate and jasper, using them to mark ownership and authority. In ancient China, jade was valued above all, considered the stone of heaven, carved into ritual objects and buried with nobility. The Aztecs and Maya used jade and turquoise in ceremonial masks and jewelry, associating green stones with water, life, and fertility. In India, the Navaratna, 9 gems, were set in jewelry to harness astrological powers. Ancient Greeks and Romans wore amethyst, believing it prevented intoxication. Across cultures, crystals were not just beautiful objects, but vessels of meaning, power, and connection to the divine. They were amulets, talismans, symbols of status, and tools of ritual. The human relationship with crystals is ancient and deep, rooted in the understanding that these enduring, beautiful objects hold something special, whether spiritual, aesthetic, symbolic. They connect us to earth, to history, and to each other. Medieval Europeans believed gems held healing and protective properties. During the Middle Ages, lapidaries, books describing the properties of stones, circulated widely. These texts attributed healing powers to various gems. Emerald was thought to improve eyesight and cure diseases. Sapphire protected against poison and brought divine favor. Diamond granted courage and invincibility. Ruby signaled danger by changing color. These beliefs blended ancient traditions with Christian symbolism. Gems adorned religious relics and ecclesiastical regalia, their value both material and spiritual. Kings and bishops wore gem-encrusted crowns and rings, not just for display, but for protection and legitimacy. Amethyst, associated with piety, was favored by clergy. Gemstones were ground into powders and consumed as medicines, a practice dangerous with some stones, but reflecting the belief in their intrinsic power. Alchemy, which sought to transform base materials into gold, also explored the transmutation of stones. These medieval ideas seem quaint today, but they reveal a worldview where minerals were active participants in the cosmos, not inert objects. They were intermediaries between the earthly and the divine, between matter and spirit. Crystals have been used as currency and trade goods. Long before coined money, valuable stones served as currency. Obsidian blades and tools were traded across prehistoric Europe. Jade was so precious in ancient China that it functioned as wealth, given as tribute and exchanged in trade. Turquoise moved along trade routes from the American Southwest to Mesoamerica. Lapis lazuli from Afghanistan reached Egypt and Mesopotamia, traded across vast distances. In some cultures, rare shells and polished stones served as money. The value of crystals made them portable wealth, durable and universally appreciated. Unlike perishable goods, crystals don't spoil. Unlike metals, some crystals are harder to work, retaining value through scarcity and beauty. Salt, a crystal, was so valuable that Roman soldiers were paid in it, giving us the word salary. Trade routes followed sources of precious stones, connecting distant peoples. The Silk Road carried not just silk, but jade, lapis, and other gems. These crystals were more than commodities. They were connections, physical objects that moved between hands and cultures, carrying value, meaning, and beauty across the ancient world. Crystals played roles in ancient and medieval medicine. Pliny the Elder's Natural History described the properties of stones, including their supposed medicinal uses. Grinding gemstones into powders and mixing them into potions was common. Pearls were dissolved in vinegar and drunk. Coral was powdered and used as a remedy. While many of these practices were ineffective or harmful, they reflected a belief that minerals held essences that could heal. Crystal, elixirs, water in which stones had been soaked, were consumed for various ailments. Amulets of specific stones were worn to prevent disease or injury. These practices persisted into the Renaissance and beyond. Even as chemistry and medicine advanced, the allure of crystal healing remained. Today, crystal healing has seen resurgence, though modern medicine does not support claims of healing properties beyond placebo effects. The historical use of crystals in medicine is a testament to humanity's desire to harness nature's beauty and rarity for health and well-being. It shows how material and symbolic value intertwine, how the physical and metaphysical can merge in human perception. The Hope Diamond carries a legendary curse. The Hope Diamond, a 45-carat blue diamond, is one of the most famous gems in the world. Its deep blue color comes from trace boron. According to legend, the diamond was stolen from a statue of a Hindu goddess and cursed those who possessed it. While the curse is likely a fabricated tale to add mystique, the diamond's history is real and storied. It was acquired by French merchant Jean-Baptiste Tavernier in India, sold to King Louis XIV, and later cut down. During the French Revolution, it was stolen and disappeared for decades. It resurfaced in London, owned by banker Henry Hope, giving the diamond its name. Subsequent owners experienced misfortunes, fueling curse rumors. Eventually, jeweler Harry Winston donated it to the Smithsonian, where it now resides, displayed for millions to admire. The Hope Diamond represents how crystals capture human imagination, how stories and history accrue around beautiful objects, transforming them into more than minerals, into legends. Whether cursed or not, the Hope Diamond is a masterpiece of nature and human craft, a tangible connection to history, power, and mystery. Crown jewels around the world feature spectacular crystals. The regalia of monarchies glitter with some of the finest gemstones ever found. The British crown jewels include the Cullinan diamond, the largest gem-quality rough diamond ever discovered. It was cut into several stones, the largest set in the sovereign's scepter. The Koh-i-Noor, a large diamond with a turbulent history, now sits in the Queen Mother's crown. The imperial state crown is adorned with thousands of diamonds, sapphires, emeralds, rubies, and pearls. Iran's crown jewels include the Darya-i-Noor, a massive pale pink diamond, and the Peacock Throne, encrusted with gems. Russia's imperial regalia featured countless gems before the revolution. These crown jewels are not merely decorations. They symbolize power, legitimacy, and continuity. They are physical manifestations of sovereignty. Throughout history, conquering powers seized gems from defeated enemies, adding them to their own treasuries. These stones have witnessed coronations, wars, and revolutions. They are as much historical artifacts as they are treasures. The crystals in crown jewels have been mined, cut, set, stolen, gifted, and revered, passing through centuries and hands, each one a participant in the unfolding story of nations. The Smithsonian houses the world's finest mineral and gem collection. The National Museum of Natural History's collection includes over 380,000 mineral specimens and 10,000 gems. Among the highlights are the Hope Diamond, the Dom Pedro Aquamarine, a stunning blue-green crystal over a foot tall, the largest faceted gem aquamarine, the Hooker Emerald, a 75-carat Colombian emerald brooch, and the Star of Asia, a 330-carat star, sapphire. The collection spans crystals from around the world, showcasing diversity, beauty, and geological significance. Museums like the Smithsonian preserve these specimens for study and public enjoyment, ensuring that rare and beautiful crystals are accessible to all, not hidden in private vaults. These collections educate, inspiring future geologists and simply delighting visitors. Walking through such a gallery is walking through Earth's treasures, seeing the best examples of what nature can create. Each specimen represents a unique combination of chemistry, time, and chance. Together, they tell the story of Earth's mineralogy, a library written in crystal, a museum of the planet's creative capacity. Indigenous peoples of the Americas valued turquoise and jade above gold. When Spanish conquistadors arrived in the Americas, they sought gold. The indigenous peoples, however, valued turquoise and jade far more. In the Southwest, Puebloan peoples and Navajo artisans crafted turquoise into intricate jewelry and ceremonial objects. Turquoise symbolized sky and water, life and fertility. In Mesoamerica, jade was the most precious material, reserved for royalty and gods. The Maya and Aztec carved jade into masks, jewelry, and ritual objects, considering it a symbol of life and power. Gold was used, but jade held deeper significance. When Cortés met Montezuma, gifts of jade were offered, objects of immense cultural value. The Spanish melted down gold, but often discarded jade, not understanding its worth. This difference in value systems highlights how culture shapes the perception of materials. What is precious is not universal, but contextual. For Europeans, gold's rarity and utility as currency made it supreme. For indigenous Americans, turquoise and jade's color, beauty, and spiritual associations held greater meaning. These crystals were links to the cosmos, to ancestors, to the forces that sustained life. Crystals have been used in timekeeping for decades. Quartz crystals revolutionized timekeeping. When an electric current is applied, quartz vibrates at a precise frequency due to its piezoelectric properties. This consistent vibration can be counted, creating an accurate time signal. Quartz watches, introduced in the 1970 seconds, were more accurate and cheaper than mechanical watches, transforming the industry. Today, nearly every digital clock relies on a tiny quartz crystal oscillator. This application turned quartz from a common mineral into an essential component of modern life. Before quartz, mechanical clocks relied on pendulums and springs, accurate but sensitive to temperature and wear. Quartz offered stability and precision. Atomic clocks are even more accurate, but quartz remains the standard for everyday timekeeping. It's remarkable that a mineral, formed over millennia in Earth's crust, now helps humanity measure seconds. The same crystal you might find on a hike regulates the time on your wrist. This intersection of geology and technology reveals how understanding natural materials leads to innovation. Quartz's structure, stable and predictable, makes it the metronome of the modern world. Silicon from quartz is the foundation of modern electronics. Nearly all electronics rely on silicon, and silicon comes primarily from quartz. Quartz is melted at high temperatures to produce metallurgical-grade silicon, which is then refined to extreme purity for semiconductor use. This pure silicon is grown into large single crystals, sliced into wafers, and processed into integrated circuits, the chips that power computers, phones, and countless devices. Without quartz, the digital age would not exist. The journey from mineral to microchip is complex, involving chemistry, engineering, and precision manufacturing. Yet it begins with one of Earth's most common minerals, silicon dioxide. The abundance of quartz made silicon technology economically viable. Sand, composed largely of quartz, is the raw material. This means the beach beneath your feet and the phone in your hand are connected, both made from the same element, arranged differently. Crystals, specifically quartz, underpin modern civilization in ways invisible but essential. Every time you use a computer, you're relying on silicon from ancient quartz, transformed through human ingenuity into technology. Diamonds are used industrially for cutting and drilling. Most diamonds are not gem quality and instead serve industrial purposes. Diamond's extreme hardness makes it ideal for cutting, grinding, and drilling. Industrial diamonds are used in saw blades to cut concrete, stone, and metal. Diamond drill bits bore through rock in mining and oil exploration. Diamond abrasives polish lenses, gems, and precision components. Synthetic diamonds, created under high pressure and temperature, are often used for industrial applications because they can be manufactured to specifications and are cost-effective. Industrial diamond consumption far exceeds gem diamond use. These unglamorous stones, small and often imperfect, do the heavy lifting of modern industry. They cut, they grind, they endure. While gem diamonds symbolize luxury and romance, industrial diamonds symbolize utility and resilience. The same crystal structure that creates brilliance in a jewel creates toughness in a tool. This duality shows crystals' versatility, beauty, and function residing in the same atomic arrangement. Diamonds are not just precious, they are practical, essential to building and shaping the world. Synthetic crystals are grown for gems and industry. Humans have learned to grow crystals, replicating natural processes in laboratories. Synthetic quartz is grown for use in electronics. Synthetic diamonds are created for industrial use and, increasingly, as gemstones. Synthetic ruby, sapphire, and emerald are produced for jewelry, offering beauty at lower cost. These lab-grown crystals are chemically and structurally identical to natural ones. They have the same properties, the same brilliance, the same durability. The difference lies in origin, not nature. Synthetic gems allow more people to enjoy the beauty of crystals without the environmental and ethical concerns of mining. They also enable industrial applications that would be impossible with rare natural stones. Some purists argue that natural gems are more valuable because of their rarity and geological journey. Others embrace synthetics as sustainable and ethical. Both perspectives have merit. Synthetic crystals are human, creations inspired by nature, evidence of our ability to understand and replicate Earth's processes. They blur the line between natural and artificial, challenging us to define what makes a crystal valuable. Cubic zirconia is a synthetic diamond simulant, not natural. Cubic zirconia, or CZ, is a synthetic material created to mimic diamond. It is zirconium oxide, stabilized with other elements to prevent phase changes. CZ is optically brilliant, with high refractive index and dispersion, creating fire and sparkle. It is hard, about 8 to 8.5 on the Mohs scale, durable enough for jewelry. To the untrained eye, CZ can resemble diamond. However, it is heavier, less hard, and under examination shows different optical properties. CZ is not a crystal found in nature, though zirconia exists in other forms. It is entirely man-made, grown from molten material. CZ made diamond. Like jewelry, accessible and affordable. Though some see it as imitation rather than gem, it serves a purpose, providing beauty without the cost. CZ is honest in its identity, a synthetic, created for a specific role. It is not trying to deceive, but to fulfill a desire for brilliance. In this, it succeeds. CZ is a reminder that beauty can be engineered, that human creativity can produce objects of aesthetic value, even when nature did not. Crystals exhibit symmetry based on their internal structure. One of the defining features of crystals is symmetry. Their internal atomic order creates external symmetry in shape. This symmetry can be rotational, where rotating the crystal a certain angle makes it look the same. It can be reflective, where one half mirrors the other. Crystallographers classify crystals into 7 systems and 32 classes based on symmetry. This classification reveals that despite the infinite variety of crystal shapes, they all conform to a limited set of symmetries. A cube, for example, has multiple axes of symmetry. A hexagonal prism has 6-fold symmetry. Even irregular-looking crystals, when examined carefully, reveal underlying symmetry. This connection between internal order and external form is profound. It shows that structure dictates appearance, that the microscopic arrangement of atoms manifests as macroscopic geometry. Symmetry in crystals is not coincidental, but inevitable, a reflection of how atoms pack most efficiently and stably. It is one of nature's most elegant demonstrations of order, visible in every crystal face and edge. Twinned crystals form when 2 crystals grow together in symmetrical ways. Sometimes during growth, 2 or more crystals join in specific, symmetrical orientations, forming twins. Twinning is not random. It follows crystallographic rules. Contact twins share a face, with one crystal's orientation rotated relative to the other. Penetration twins appear to pass through each other. Repeated twinning creates multiple individuals in a regular pattern. Some minerals twin frequently. Quartz shows Dauphiné twins, where 2 crystals interpenetrate. Gypsum forms swallowtail twins, V-shaped pairs. Calcite produces butterfly twins. These twins are not defects, but natural variations. They often create more complex and interesting shapes than single crystals. Twinning arises from errors during growth, when atoms settle into alternate orientations that happen to fit together. The result is crystals that look conjoined, faces meeting at unusual angles, symmetry multiplied. Collectors prize twins for their uniqueness. Twinning shows that even rigid rules allow for variation, that within the constraints of structure, creativity emerges. It is a reminder that nature works within laws, but still finds ways to surprise. Crystal faces grow at rates determined by atomic structure. Each face on a crystal represents a plane of atoms. Depending on how atoms are arranged in that plane, growth can be fast or slow. Tightly packed planes with few bonding sites grow slowly, remaining prominent. Loosely packed planes grow quickly and shrink or disappear. This principle explains why crystals develop the shapes they do. The faces you see are the slow-growing ones. This relationship between atomic structure and macroscopic form is central to crystallography. By studying crystal shapes, scientists can infer internal structure. Conversely, knowing structure allows prediction of shapes. In gem cutting, understanding which faces are more stable helps maximize durability. In crystal growing, controlling conditions can favor desired faces. Every angle, every edge on a crystal is a direct expression of atoms and bonds, invisible forces made visible. To hold a crystal is to hold geometry dictated by chemistry, form following function at the atomic level. The elegance of this connection is one of crystallography's deepest insights. Cleavage describes how crystals split along specific planes. Some crystals break along smooth, flat surfaces called cleavage planes. These correspond to directions where bonds are weakest. Mica cleaves perfectly into thin sheets. Halite cleaves into cubes. Fluorite cleaves into octahedrons. Other crystals have no cleavage and fracture irregularly, like quartz. Cleavage is a diagnostic property, helping mineralogists identify specimens. It also matters for gem cutters, who must consider cleavage to avoid splitting stones during cutting. Diamonds have perfect cleavage in 4 directions, a property used historically to split rough diamonds before soaring technology. A single blow along a cleavage plane can divide a diamond cleanly. Topaz's perfect cleavage makes it somewhat fragile despite hardness. Cleavage reveals that crystals are not uniformly strong in all directions. Their internal structure creates planes of weakness. Understanding cleavage is understanding vulnerability, the places where order is most easily disrupted. Yet cleavage also creates beauty. The clean splits and shiny surfaces that reveal crystal interiors, fresh and unweathered. Fracture describes how crystals break when not along cleavage. When a crystal breaks in directions other than cleavage, it fractures. Fracture can be conchoidal, smooth and curved like glass, common in quartz and obsidian. It can be uneven or splintery. Fracture patterns provide clues to a mineral's structure and toughness. Even minerals with good cleavage can fracture if struck at the wrong angle. Fracture surfaces are generally rough and less shiny than cleavage surfaces. In gemstones, fracture can reduce value, but in some cases, it creates interest. Natural fractures sometimes heal with secondary minerals, creating inclusions. Understanding fracture helps in working with crystals, knowing how they will respond to stress. It also reveals that while crystals have internal order, they are still solid materials subject to physical laws. They can break, chip, shatter. This fragility contrasts with their enduring nature, a reminder that even ancient, hard materials are not indestructible. Yet often, broken crystals reveal interiors just as beautiful as exteriors, layers and inclusions exposed, stories previously hidden now visible. Hardness varies greatly among crystals, from talc to diamond. The Mohs scale of hardness ranks minerals from 1 to 10 based on scratch resistance. Talc, softest, is 1. Diamond, hardest, is 10. Each number can scratch those below it. Gypsum is 2, scratched by a fingernail. Calcite is 3. Fluorite is 4. Apatite is 5, barely scratched by a knife. Orthoclase is 6. Quartz is 7. Topaz is 8. Corundum is 9. Diamond is 10. This scale is relative, not absolute. The gap between corundum and diamond is larger than between talc and corundum. Hardness depends on bond strength and crystal structure. Tightly bonded structures resist scratching. Hardness affects durability and use. Soft minerals are easily carved, but don't hold detail long. Hard minerals resist wear, but are difficult to work. Gem hardness determines wearability. Stones, above 7, resist scratching from dust, which contains quartz. Softer stones need careful handling. Hardness also affects polishing. Hard stones take better polish. Understanding hardness helps in selecting and caring for crystals. Luster describes how light reflects from a crystal's surface. Luster is the quality of light reflected from a mineral's surface. Metallic luster, like pyrite or native copper, resembles polished metal. Non-metallic lusters include vitreous, glassy, like quartz, resinous, like sulfur, pearly, like talc, silky, like fibrous gypsum, greasy, like nephrite jade, adamantine, brilliant like diamond. Dull or earthy luster appears in non-crystalline or weathered minerals. Luster depends on how light interacts with the surface, influenced by reflectivity and surface structure. Metallic minerals contain opaque materials with free electrons that reflect light efficiently. Adamantine luster results from high refractive index. Like diamond, luster is a quick diagnostic tool, helping identify minerals. It also affects aesthetic appeal. Glassy crystals feel modern and clean, metallic ones dramatic and striking, silky ones soft and organic. Luster adds another layer to how we perceive crystals, how they catch and return light, whether they glow, gleam, shimmer, or shine. It is part of their character, as defining as color or form. Inclusions tell stories of a crystal's formation conditions. Trapped within crystals are inclusions, foreign materials engulfed during growth. These can be tiny crystals of other minerals, bubbles of gas, droplets of liquid, or even organic matter, far from floors. Inclusions are time capsules, preserving information about formation conditions. Fluid inclusions contain ancient water or gases from when the crystal formed. By heating these inclusions and observing when the liquid and vapor phases merge, scientists estimate formation temperature. Some inclusions contain multiple phases, liquids, gases, and solid crystals coexisting in a tiny cavity. These provide insights into pressure and chemistry. Mineral inclusions reveal what was present in the environment. Rutile needles in quartz indicate high temperatures. Bubbles in amber preserved ancient air, allowing study of past atmospheres. Inclusions also create aesthetic effects. Rutilated quartz, moss agate, and star gems. They turn crystals into windows into the past, showing us moments frozen in time. Each inclusion is a message, written in matter, from Earth's interior or ancient seas, preserved unchanged across millennia. Phantom crystals show evidence of interrupted growth. Sometimes during crystal growth, conditions change, growth pauses, and the crystal surface is lightly dusted with impurities. When growth resumes, a new layer forms over the dusted surface, creating a ghostly outline of the earlier shape inside. These are called phantom crystals. The phantom appears as a faint image within the crystal, often a different color. Multiple phantoms can occur, each recording a pause in growth. They reveal that crystal formation is not always continuous, but can be episodic, responding to changing environment. Looking at a phantom crystal is like seeing its past selves, layers of history visible simultaneously. It's a geological echo, earlier stages preserved within later ones. Phantoms are prized by collectors for their visual interest and the story they tell. They remind us that crystals are dynamic, that their growth can stop and start, influenced by forces beyond our view. Each phantom is a chapter, the moment in time when conditions shifted, written in mineral and visible in the final form. Growth zones sometimes create color banding in crystals. As crystals grow, Varying conditions create layers with slightly different compositions, leading to color banding. Agate is the classic example, concentric bands of different colors. Amethyst sometimes shows color zones, darker and lighter areas corresponding to growth periods. Sapphire can have zones of varying color, complicating cutting. These bands follow the crystal's shape, outlining faces that existed at different stages. The banding is a growth record, each zone a snapshot of the environment when that layer formed. Changes in temperature, pressure, or chemical availability all leave marks. By studying these zones, geologists reconstruct the history of crystal formation. For gem cutters, banding affects how stones are cut, as orientation determines which colors are visible. For collectors and observers, banding adds complexity and interest. It makes the crystal a layered narrative, not a uniform object. Each band is a sentence in the story of its creation. Stripes of time solidified in mineral form. Crystals can heal. Fractures with new mineral growth. Crystals can crack from stress, but sometimes these fractures heal. Mineral-rich fluids seep into cracks and deposit new material, cementing the fracture. The healing mineral may be the same as the host crystal or different, creating visible lines or inclusions. Healed fractures, called negative crystals when hollow voids fill, or feathers when partially filled, are common in quartz. They appear as internal streaks or clouds, often with interesting shapes. These healed zones can be iridescent, refracting light into rainbow colors. The healing process shows that crystals, though solid, can change and grow even after initial formation. They are not static, but continue responding to their environment. A fractured crystal that heals is a survivor, marked but whole, its history visible in the scar. For geologists, healed fractures provide insights into tectonic events, fluid flow, and post-formation processes. For admirers, they add character, evidence of a crystal's resilience, beauty marked by its trials. Some crystals form pseudomorphs, replacing other minerals. A pseudomorph is a crystal that has the outward shape of one mineral, but the composition of another. This occurs when one mineral replaces another, atom by atom, preserving the original shape. For example, quartz can replace fluorite, creating quartz crystals in cubic shapes. Fluorites form. Pyrite can replace fossils, creating golden replicas. Malachite can replace azurite, or vice versa, as weathering conditions change. Pseudomorphs are mineralogical puzzles, form and content mismatched. They reveal that minerals are not permanent but can transform, structures acting as templates even as chemistry changes. Pseudomorphs require specific conditions, fluids carrying new elements while removing old ones, a slow atom-by-atom exchange. The result is a mineral that looks wrong, a shape that doesn't match the composition. For collectors, pseudomorphs are fascinating oddities. For scientists, they are clues to geochemical processes, to how minerals react and replace each other in Earth's dynamic system. They show that identity is not just structure or composition, but both. And when they diverge, something strange and wonderful emerges. Crystals are studied using X-ray diffraction to reveal structure. The internal structure of crystals, invisible to the eye, can be mapped using X-ray diffraction. When X-rays pass through a crystal, they diffract, bending and creating patterns of spots or rings on a detector. These patterns reflect the spacing and arrangement of atoms. By analyzing the diffraction pattern, scientists determine the crystal's atomic structure, the exact positions of atoms in 3 dimensions. This technique, developed in the early 20th century, revolutionized crystallography and chemistry. It revealed the double helix of DNA, the structures of proteins, and the arrangements of atoms in countless minerals. X-ray diffraction proves that crystals are ordered, not random, and allows precise measurement of that order. It connects the macroscopic, the crystal you hold, with the microscopic, the atomic lattice you cannot see. This technique transformed crystals from objects of beauty and curiosity into keys to understanding matter itself. Every crystal structure known today was determined using X-ray diffraction or related methods, making it one of science's most powerful tools. Crystals grow larger when cooling or evaporation is slow. The size a crystal reaches depends on how long it has to grow. Slow cooling in magma chambers allows atoms to settle into place over millennia, producing large crystals like those in granite or pegmatite. Fast cooling, like lava erupting, leaves little time, creating tiny crystals or glass. Similarly, slow evaporation of water allows large salt or gypsum crystals to form. Rapid evaporation creates tiny grains. Time and stability are key. Uninterrupted growth in a stable environment produces the best crystals, well-formed and large. Disturbances, changes in temperature, pressure, or chemistry interrupt growth or cause defects. The giant crystals in caves and pegmatites are products of extraordinary patience, conditions held constant for ages. In laboratories, growing large crystals requires careful control, maintaining temperatures and supersaturation for weeks or months. The largest natural crystals are older than civilizations, slow accumulations of matter, atom by atom. They remind us that greatness often requires time, that patience yields size and perfection, that the best things grow slowly. Geodes form when mineral-rich water fills hollow spaces. Geodes are nature's treasure boxes, unremarkable rocks on the outside, lined with crystals inside. They form when gas bubbles or voids in volcanic or sedimentary rock fill with mineral-rich water. Over time, minerals precipitate on the cavity walls, layer by layer, growing inward. The crystals point toward the center, creating a sparkling interior. Amethyst geodes, quartz geodes, and calcite geodes are common. Some geodes are lined with agate, others with druzy quartz. Thousands of tiny glittering points. Geodes can be small as a fist, or large enough to stand inside. Breaking or cutting a geode open reveals the hidden treasure, a moment of anticipation and discovery. Each geode is unique, its interior shaped by the specific conditions of formation, the chemistry of the water, the minerals available, the time allowed. Geodes symbolize hidden beauty, the idea that unassuming exteriors can conceal wonders. They invite us to look deeper, to crack open the ordinary and find the extraordinary within. They are reminders that beauty often hides, waiting to be discovered. Stalactites and stalagmites are calcite formations in caves. In limestone caves, water seeping through rock dissolves calcite. When the water drips from the ceiling into a cave, carbon dioxide escapes, reducing the water's ability to hold dissolved calcite. The calcite precipitates, forming stalactites, icicle-like formations hanging from the ceiling. Drips that reach the floor deposit calcite there, building stalagmites upward. Over thousands of years, these grow, sometimes meeting to form columns. The process is slow, adding a thin layer with each drip. Stalactites and stalagmites are made of countless tiny calcite crystals, fused together into solid masses. They form flowstone, draperies, and other speleothems, cave decorations shaped by flowing water. Their colors range from white to orange, brown, or even translucent. Impurities and variations in water chemistry create banding and hues. Cave formations are fragile, easily damaged, and take immense time to form. Breaking one destroys thousands of years of growth. Protected caves allow visitors to witness these natural sculptures. Calcium carbonate art, created by water, time, and chemistry. Endlessly patient, endlessly intricate. Hot springs deposit minerals, creating colorful terraces. In geothermal areas, hot water rises from deep underground, carrying dissolved minerals. As the water reaches the surface and cools, it can no longer hold as much dissolved material. Minerals precipitate, forming deposits around the spring. Travertine terraces, made of calcite, build up in layered pools, each one edged with delicate mineral rims. Yellowstone's hot springs are famous for colorful deposits, not only minerals but also thermophilic bacteria that thrive in hot water, adding yellows, oranges, greens, and browns. Silica deposited from hot springs forms sinter, also called geyserite, creating mounds and terraces around geysers. Mammoth Hot Springs in Yellowstone is a spectacular example. White terraces cascading down the hillside. These deposits grow visibly, layers accumulating over years rather than millennia. The combination of mineral precipitation and microbial mats creates alien landscapes, colorful, steaming, and otherworldly. Hot springs are active crystallization sites, places where Earth's interior delivers material to the surface, where water and rock interact, creating beauty from chemistry and temperature. Petrified wood is fossilized wood replaced by minerals. Petrified wood forms when fallen trees are buried in sediment. Mineral-rich water percolates through the wood, and minerals, often silica, replace the organic material cell by cell. The result is wood turned to stone, preserving the texture, rings, and even cellular structure in crystalline form. Petrified wood can be incredibly detailed, showing bark, knots, and growth patterns. The 15 colors depend on the minerals involved. Iron oxides create reds and yellows, manganese creates pinks and purples, copper creates greens and blues. Entire petrified forests exist, fields of ancient logs turned to stone, windows into prehistoric ecosystems. Arizona's Petrified Forest National Park contains logs from trees that lived over 200 million years ago, now solid, agate, or jasper. Holding petrified wood is holding organic and mineral history merged, life transformed into crystal, a bridge between living and non-living. It reminds us that minerals can preserve, that stone can remember, that even the most transient things, like wood, can become permanent if the conditions are right. Fossils are sometimes preserved or replaced by crystals. Beyond petrified wood, many fossils are preserved or replaced by minerals. Shells may be replaced by calcite or pyrite, preserving intricate details. Ammonites, ancient marine creatures, are sometimes preserved in aragonite or replaced by pyrite, creating golden fossils. Shells filled with sediment can become geodes, hollow inside with quartz or calcite crystals lining the interior. Some fossils are preserved in amber, fossilized tree, resin, insects, and plants trapped and preserved in exquisite detail. Amber is organic, not crystalline, but it often contains bubbles and inclusions, tiny windows into ancient ecosystems. Opal sometimes replaces fossils in Australia, creating opalescent shells and bones, shimmering with color. These opal fossils are both fossil and gemstone, beauty and science merged. Mineral preservation allows us to study extinct life, to see organisms that lived millions of years ago, their forms captured in stone. Crystals become storytellers, holding the shapes of the past, giving us access to lost worlds through their enduring structures. The formation of crystals involves supersaturation of solutions. For a crystal to form from a solution, the solution must be supersaturated, meaning it holds more dissolved material than it normally could at equilibrium. Supersaturation is achieved by cooling, evaporation, or chemical reaction. Once supersaturated, dissolved ions or molecules begin to cluster, forming nuclei. Some nuclei dissolve, but if they reach a critical size, they grow into crystals. Molecules from the solution attach to the nucleus, layer by layer, following the lattice pattern. Supersaturation drives growth. The greater the supersaturation, the faster the growth. However, very fast growth can lead to poorly formed crystals with defects. Moderate supersaturation allows well-ordered growth. Controlling supersaturation is key in crystal growing, whether in nature or labs. Too little, and growth stops. Too much, and crystals form too quickly and imperfectly. Nature often achieves a balance, creating conditions where slow, steady growth produces beautiful, well-formed crystals. Understanding supersaturation is understanding the chemistry of crystallization, the delicate balance between solution and solid, between disorder and order. Temperature and pressure profoundly affect crystal formation. The same chemical composition can form different minerals under different conditions. Carbon becomes graphite at low pressure, diamond at high pressure. Calcite is stable at low temperature, aragonite at higher temperature and pressure. These polymorphs, same composition, different structure, show that temperature and pressure dictate which arrangement is stable. Changing conditions can transform one mineral into another. Metamorphism exploits this. Pressure and temperature reorganizing minerals without melting. Phase diagrams map which minerals are stable at which conditions, guiding geologists in understanding rock history. For crystal growers, controlling temperature and pressure allows synthesis of specific minerals. Industrial diamond production uses high-pressure presses replicating mantle conditions. Understanding how temperature and pressure influence crystallization helps predict what minerals form where, how rocks evolve, and how to recreate nature's processes. It reveals that crystals are not arbitrary, but products of specific environments, each one a record of the temperature and pressure under which it formed. A snapshot of Earth's interior conditions, encoded in atomic arrangement. Some crystals exhibit optical phenomena, like asterism or chatoyancy. Certain crystals display optical effects beyond simple transparency or color. Asterism, the star effect seen in star sapphires and rubies, results from oriented needle-like inclusions that reflect light into a star pattern. Chatoyancy, the cat's eye effect, comes from parallel fibers or tubes within the crystal, creating a band of light that moves across the surface. Both effects require specific cutting, cabochons, rather than facets, to display properly. These optical properties add value and fascination. Light interacts with internal structures in complex ways, creating effects that seem almost magical. Aventure sense, the sparkle in aventurine. Quartz comes from tiny reflective inclusions, usually mica. Labradorescence, the play of color in labradorite, results from light scattering from internal layers. These phenomena show that crystals are not just static forms, but interactive objects. They respond to light dynamically, changing appearance with angle and illumination. They remind us that beauty is not fixed, but relational, emerging from the interaction between object and observer, between structure and light. Crystals can be irradiated to change color. Exposure to radiation can alter crystal color by creating or changing color centers. Natural radiation from surrounding rock slowly colors smoky quartz. Artificial irradiation accelerates this, turning clear quartz smoky or brown. Blue topaz is almost always created by irradiating colorless topaz, followed by heating to stabilize color. This treatment is permanent and safe after a short decay period. Some gemstones change color when irradiated, others don't. Diamonds can be irradiated to turn them green, though the color may not be stable. Kunzite and some beryls can be altered. Irradiation treatment is disclosed in the gem trade, though not always to end consumers. The practice shows how humans can manipulate crystal properties, harnessing physics to alter appearance. It also raises questions about value and authenticity. Is an irradiated stone less valuable than a naturally colored one if they're visually identical? Opinions vary. What's clear is that irradiation is part of modern gemology, a tool for enhancing material, making beautiful stones from material that might otherwise be discarded. It bridges science and art, physics and aesthetics. Heat treatment is common in gemstones to improve color. Heating gemstones is one of the oldest treatments used for centuries to enhance color. Citrine is usually heat-treated amethyst. Blue sapphire is often heated to deepen color and remove silk, needle-like inclusions. Ruby is heated to dissolve inclusions and improve color. Tanzanite is heated to shift its color from brownish to the color desired blue-violet. Heat treatment is stable. The change is permanent. It is widely accepted in the trade, though disclosure is required for valuable stones. Heating mimics natural processes. Temperatures used are similar to those in Earth's crust. In a sense, it's accelerating what might have happened naturally, given more time or slightly different conditions. Not all stones respond to heating, and skill is required to avoid damage. Too much heat can crack or discolor stones. Done properly, heat treatment reveals potential, enhancing beauty that was latent. It shows human agency in working with nature, not against it. Using heat as a tool to unlock colors that the stone could display under the right circumstances. Crystals are used in lasers, amplifying light through their structure. Certain crystals can amplify light, making them essential for lasers. Ruby was used in the first laser. Its chromium atoms excited by light, then releasing photons in a coherent beam. YAG, neodymium, doped yttrium aluminum garnet, is a common laser crystal. Sapphire, titanium-doped sapphire, is used in tunable lasers. These synthetic crystals are grown specifically for optical properties. The crystal structure allows stimulated emission, where photons encourage atoms to release more photons of the same wavelength and phase. The result is a concentrated, coherent beam of light. Lasers have countless applications: surgery, cutting, communication, measurement. The crystals, at their hearts, are key components, chosen for their optical and thermal properties. Crystals in lasers show how structure at the atomic level enables macroscopic technologies. They turn crystals into tools that shape light, enabling precision and power. It's a marriage of physics and crystallography, where understanding atomic arrangements allows manipulation of photons, light bent to human will through the medium of crystal. Liquid crystals are states of matter between liquid and solid. Liquid crystals are not crystals in the traditional sense, but phases of matter with properties between liquids and crystals. Their molecules can flow like liquids but maintain some orientational order like crystals. This gives them unique optical properties used in LCD screens. By applying electric fields, the orientation of liquid crystal molecules can be controlled, changing how light passes through. This allows pixels to turn on and off, creating images. Liquid crystals revolutionize displays, enabling flat screens for computers, phones, and TVs. Though different from mineral crystals, the term acknowledges their partial order. Liquid crystals show that matter can exist in intermediate states, not fully ordered but not fully disordered. They expand the concept of crystallinity beyond rigid solids, reminding us that phases of matter are more varied than simple solid, liquid, gas. They also show how understanding materials at the molecular level enables technology, turning abstract science into everyday tools, screens that display information, all thanks to molecules that flow yet align. Some crystals are hygroscopic, absorbing water from the air. Certain crystals attract moisture from the air, a property called hygroscopy. Halite, table salt, is hygroscopic, which is why salt clumps in humid weather. Borax and some other minerals also absorb moisture. Hygroscopic crystals can deliquesce, absorbing so much water they dissolve into solution. This makes them difficult to store without protection. In humid environments, hygroscopic crystals need sealed containers to prevent damage. This property shows that crystals are not inert, but interact with their environment. They respond to humidity, temperature, and atmospheric composition. Some crystals, like zeolites, have porous structures that trap water molecules. These are used as desiccants, drying agents that absorb moisture, or in catalysis, where trapped molecules react. Hygroscopy reveals that crystal surfaces and structures are active, engaging with surrounding molecules, pulling them in or releasing them. It reminds us that crystals are part of a dynamic system, not isolated objects, but participants in chemical exchanges with their surroundings. Crystals can exhibit fluorescence, glowing under UV light. Many minerals fluoresce, emitting visible light when exposed to ultraviolet light. This fluorescence comes from impurities or defects in the crystal structure. UV photons excite electrons to higher energy levels, and when they drop back, they release visible light. Fluorite, calcite, willemite, and many others fluoresce in vivid colors. Some diamonds fluoresce blue, a property used in identification. Fluorescence can be strong or weak, and not all specimens of a mineral fluoresce equally. Collecting under UV light is a hobby, revealing hidden colors invisible in daylight. Museums sometimes have UV displays showing glowing minerals, an otherworldly sight. Fluorescence adds a hidden dimension to crystals, beauty revealed only by changing the light. It shows that crystals hold more than meets the eye, that they can surprise us, that their properties extend beyond the visible spectrum. Fluorescence is light remembered and returned, energy absorbed and re-emitted, a conversation between crystal and photon, invisible made visible. Crystals form the mountains, the bedrock, the very ground beneath our feet. When we think of crystals, we often picture gemstones or mineral specimens in cases, but crystals are everywhere, the foundation of all rocks. Mountains are piles of interlocking crystals, granite peaks built from quartz, feldspar, and mica. Basalt flows are mosaics of tiny crystalline grains. Even soil contains microscopic crystals, clay minerals, and weathered fragments. The ground you walk on, the cliffs you admire, the stones in rivers, all are crystals or made of crystals. This ubiquity means crystals are not rare exceptions, but the rule. Earth's crust is a crystalline shell, varied in form, but unified in structure. Understanding this transforms our relationship with the landscape. Every pebble is a crystal or assemblage of crystals. Every grain of sand is quartz, a crystal worn smooth. The planet itself is built from atomic order, repeated endlessly, layers upon layers of mineral crystals forming the solid Earth. We live on a crystalline world, our homes and roads built from materials quarried from crystalline rock, our lives supported by a foundation of ordered atoms. The beauty of crystals has inspired artists, jewelers, and craftspeople. Throughout history, the beauty of crystals has inspired human creativity. Ancient artisans carved jade, lapis, and turquoise into objects of art. Jewelers set gemstones into crowns, rings, and necklaces, enhancing their natural beauty with metalwork. Sculptors carved marble and alabaster, shaping crystalline rock into statues that lasted millennia. In the modern era, artists use crystals in installations, capturing light and color in new ways. Glassmakers have mimicked crystal clarity, creating lead crystal that sparkles like gemstones. The faceting of gems is an art, cutters studying each stone to maximize brilliance and color. Traditional cuts, like brilliant, emerald, and cabochon, evolved to showcase specific properties. Modern cutting includes fantasy cuts, unusual shapes that push boundaries. Crystals provide both material and inspiration, their geometry and color influencing design. Art Deco borrowed from crystal angles, creating geometric patterns. Crystal chandeliers refract light into rainbows, decorating palaces and halls. The interplay between natural crystal beauty and human artistry has produced countless works, each one celebrating the aesthetic power of ordered atoms. Crystals connect us to deep time, to Earth's ancient past. Holding a crystal is holding deep time. Many crystals are millions or billions of years old, formed in eras unimaginably distant. Zircon crystals from Australia are 4.4 billion years old, nearly as old as Earth. Diamonds are often over 1 billion years old, formed in the Archean or Proterozoic eons. Quartz crystals may have grown over millions of years in cooling magma or slowly seeping water. These are not metaphors. Crystals are genuinely ancient. They're atoms locked in place long before any form of complex life existed. They witnessed Earth's history, silent and enduring. Mountains rose and eroded, continents drifted, climates changed, species evolved and vanished, yet crystals remained. To hold one is to connect across time, to touch something that existed when the world was young. It is a tangible link to the past, a bridge between the present moment and the distant origins of the planet. Crystals teach patience, showing us that the most enduring things form slowly, that time is written in stone, that history is not just recorded in books but held in mineral form. Each crystal is unique, no two exactly alike. Though crystals follow strict geometric rules, no two are identical. Growth conditions vary, impurities differ, tiny fluctuations alter shape and size. Even crystals from the same geode or pegmatite show individuality. One may be larger, another clearer, a third show better color. Inclusions, fractures, and growth features create uniqueness. Snowflakes, ice crystals, are famously unique, each one a variation on the hexagonal theme. Mineral crystals are the same, united by structure but varied in expression. This individuality makes collecting meaningful. Each specimen is one of a kind, irreplaceable. It also makes crystals personal. The one you choose speaks to you in some way, its shape, color, or character resonating. Uniqueness within order is a paradox that crystals embody. They are governed by laws, yet infinitely varied, ordered, yet individual. This balance mirrors life itself, patterns within which endless variation occurs. Crystals remind us that rules and freedom coexist, that structure does not preclude diversity, that within the lattice of existence, each being, each crystal, is unique. Crystals teach us about the hidden order within matter. At first glance, the world seems chaotic, but crystals reveal underlying order. Atoms, invisible and tiny, arrange themselves with precision into lattices that extend in 3 dimensions. This order is not imposed from outside, but emerges from the nature of atoms and forces between them. It is self-organization, matter finding the most stable arrangement. Crystals show that order is fundamental to the universe. Stars form from collapsing gas. Galaxies spiral into organized structures. Life itself depends on molecular order. Proteins and DNA are arrangements of atoms as precise as any crystal. Crystals are a visible manifestation of this principle. They teach that even in apparent randomness, patterns exist. By studying them, we learn to see beneath surfaces, to recognize structure in nature. Crystallography, the science of crystals, has revealed the atomic structure of countless materials, advancing chemistry, physics, and biology. From crystals, we learn that matter is not continuous, but made of atoms, that these atoms have preferred arrangements, that understanding structure is key to understanding properties. Crystals are lessons in order, in the hidden architecture of the world. Collecting crystals connects people to geology, chemistry, and earth. Many people collect crystals, drawn by beauty, rarity, or scientific interest. This hobby fosters connection to earth. Collectors learn geology, how rocks form, where minerals are found, what conditions create specific crystals. They learn chemistry, understanding formulas and compositions. They visit mines, quarries, and rock shops, meeting others with shared interests. Field collecting involves hiking, exploring, searching through rock and soil, connecting physically with landscape. Even purchasing specimens connects collectors to far-off places, mines in Brazil, Afghanistan, or Madagascar. Each crystal is a piece of earth, a fragment of geology to hold and study. For children, collecting sparks curiosity about the natural world. For adults, it offers a tangible hobby, combining aesthetics, science, and adventure. Crystals are affordable and accessible. From common quartz to rare gems, there's something for every budget. They are durable, lasting indefinitely, with care. A collection becomes a personal museum, each piece telling a story, together forming a narrative of Earth's diversity. Collecting crystals is a way to engage with the planet, to appreciate its processes and products, to bring a bit of the geological world into daily life. Crystals are gifts from the earth, formed in darkness, brought to light. Most crystals form deep underground or within rock, hidden from view. Geological processes, erosion, tectonic uplift, volcanic eruptions, bring them to the surface. Mining and quarrying extract them from darkness. When we find or purchase a crystal, we are receiving something that began its journey in conditions we can barely imagine, under pressure, in heat, in the slow flow of mineral-laden water. The crystal's journey from formation to our hands is an epic spanning millennia. It formed in darkness, grew slowly, waited in rock, was eventually exposed, weathered perhaps, then found, extracted, cleaned, sold, and finally held. This journey transforms the crystal into a gift, not just a commodity. It is a gift from deep time, from Earth's interior, from processes older than humanity. Recognizing this changes how we value crystals. They are not just pretty objects, but messengers from realms we cannot visit, tangible evidence of Earth's creativity, pieces of planetary history offered up from below. Each one is a gift, freely given by geological chance, waiting to be discovered and appreciated. Crystals remind us of the connection between micro and macroscopic worlds. Crystals are bridges between scales. At the atomic level, they are arrangements of particles, electrons, protons, neutrons, organized into atoms and molecules, bonded into lattices. At the macroscopic level, they are objects we can see and hold, with faces, edges, and colors. What happens at the atomic scale determines what we observe at the human scale. The angle between faces reflects bond angles between atoms. Color comes from electron behavior. Hardness depends on bond strength. This connection is profound. It means that the invisible world of atoms, the realm of quantum mechanics, manifests as the visible world we experience. Crystals are proof that microscopic rules govern macroscopic reality. They teach that understanding the small reveals the large, that studying atoms explains stones. This principle extends beyond crystals to all matter. Everything we see is determined by what happens at scales too small to see. Crystals make this abstract idea concrete. They are lessons in causality, in how structure at one level creates properties at another. They show that the universe is coherent across scales, that the same laws apply from atoms to mountains, and that understanding requires looking both at surfaces and depths. Some cultures view crystals as spiritual or healing objects. Many cultures attribute metaphysical properties to crystals. Ancient and modern traditions hold that crystals carry energies that can influence health, mood, and spiritual state. Rose quartz is associated with love, amethyst with calm, citrine with abundance. These beliefs are not scientifically supported. No evidence shows that crystals emit energies affecting human physiology or psychology beyond placebo. Yet belief in crystal healing persists, part of broader alternative health movements. For believers, crystals are tools for meditation, focusing intention, or creating sacred space. They are used in rituals, worn as amulets, placed in homes. Skeptics argue this is superstition, attributing effects to confirmation bias and placebo. Believers argue that science doesn't measure everything, that subjective experience is valid. This debate highlights different ways of relating to crystals: material versus metaphysical, scientific versus spiritual. Regardless of one's stance, it's clear that crystals hold psychological and cultural significance for many. They comfort, inspire, and focus attention. Whether the mechanism is energy or psychology, the effect is real for those who experience it. Crystals, in this view, are not just minerals, but symbols, holders of meaning, objects through which people engage with their inner lives. Scientific study of crystals has advanced technology and medicine. Crystallography has driven technological progress. Understanding crystal structures led to semiconductors, enabling computers. X-ray crystallography revealed protein structures, advancing medicine and biology. The structure of insulin, DNA, hemoglobin, and countless drugs were determined by crystallography. This knowledge enabled design of targeted therapies, understanding diseases, and creating synthetic materials. Crystallography won multiple Nobel Prizes, recognizing its impact. Pharmaceutical companies use crystallography to design drugs that fit molecular targets precisely, like keys in locks. Materials science uses crystal knowledge to engineer metals, ceramics, and polymers with desired properties. Photonic crystals manipulate light in new ways. enabling advances in communication and computing. The humble study of mineral crystals expanded into a field that touches nearly every aspect of modern life. It shows that pure science, studying crystals for their own sake, yields practical benefits. Curiosity-driven research into crystal structures has paid dividends beyond anyone's imagination. Crystals, once admired for beauty alone, became keys to unlocking the molecular world, tools for healing and innovation. Crystals in meteorites tell us about other worlds. Meteorites, fragments of asteroids or planets that fall to Earth, contain crystals formed in space. These extraterrestrial crystals reveal conditions on other bodies. Some meteorites contain diamonds, formed in impacts or in the cores of shattered planetesimals. Others contain olivine, pyroxene, and feldspar, minerals familiar on Earth but formed in alien environments. Certain meteorites hold presolar grains, crystals older than the solar system itself, formed in other stars and carried here. These grains are stardust, tiny crystals with isotopic compositions, revealing their origins in supernovae or red giants. Studying meteorite crystals helps us understand the early solar system, how planets formed, what asteroids are made of. The crystals are samples from space delivered to us. Moon rocks brought by Apollo missions contain crystals formed in lunar basalts, from impacts, from processes unique to the Moon. Martian meteorites, blasted off Mars by impacts, contain minerals, suggesting past water, possibly past life. Crystals in meteorites are windows into the cosmos, showing us that crystallization is universal, that other worlds form minerals too, that the same physics and chemistry operate throughout the universe. Some crystals are so rare only a few specimens exist. Extreme rarity marks some minerals. Painite was once the rarest, with only a handful of specimens known. Today, a few more have been found, but it remains rare. Red beryl, found only in Utah, is exceptionally rare, most specimens tiny. Taphete, muscovite, and grandidierite are gemstones few have heard of, their scarcity making them valuable. Some minerals are known from only one location, type localities where they were first discovered, and remain unique. These rarities exist because formation requires unusual conditions, specific chemistry, and chance. They remind us that the range of minerals is still being discovered. New species, described each year. Rarity adds mystique, but also raises questions about value. Is a rare but unattractive mineral more valuable than a beautiful common one? Collectors and scientists may answer differently. Rare crystals are treasures for their scarcity, but common crystals are treasures for their beauty and abundance. Both have worth. Rarity highlights the diversity of Earth's chemistry, the countless combinations and conditions that produce minerals. It shows that even on a planet billions of years old, surprises remain. Large crystals are geological wonders, some weighing tons. While most crystals are small, some grow enormous. The largest known crystal is a beryl from Madagascar, weighing 18 tons and over 60 feet long, though not gem quality. Selenite crystals in Mexico's Cave of Crystals reach over 30 feet. Quartz crystals, weighing several tons, have been found in Brazil. Spodumene crystals over 40 feet long have been mined. These giants form in pegmatites or caves, where conditions remain stable for immense periods. Their size is staggering, demonstrating the potential of crystallization given time and space. Large crystals are often displayed in museums, marvels of natural growth. They inspire awe, challenging our sense of scale. How can something so ordered, so geometric, grow so large? The answer lies in unimaginable patience, atoms stacking one by one over eons. Large crystals are monuments to time, evidence that slow, steady processes can produce the monumental. They are nature's cathedrals, built not by hands but by chemistry, towering testaments to the power of accumulation. Microcrystals can be beautiful under magnification. Not all beauty is visible to the naked eye. Under microscopes, tiny crystals reveal exquisite forms. Snowflakes are ice crystals best appreciated magnified, showing intricate six-fold symmetry and delicate branches. Microscopic minerals form perfect geometric shapes, tiny cubes, pyramids, and prisms, invisible without magnification. Scanning electron microscopes reveal even smaller structures, nano crystals with atomic-level detail. These micro-worlds are just as ordered and beautiful as large specimens. They show that crystallization occurs at all scales, from nanometers to meters. Microscopy opened new realms of crystal study, allowing examination of thin sections of rock, identifying minerals by their optical properties, colors, and textures under polarized light. The beauty of thin sections, with their interference colors and extinction patterns, is abstract art created by crystal properties and light interaction. Microcrystals remind us that beauty exists at every scale, that the universe is fractal in a sense, patterns repeating from small to large, that paying attention to the tiny reveals wonders as great as the grand. Crystals can form in living organisms, biomineralization. Life creates crystals, a process called biomineralization. Shells are calcium, carbonate, aragonite, or calcite crystals arranged by mollusks and other sea creatures. Bones and teeth are apatite, a calcium phosphate mineral structured by cells. Corals build reefs from aragonite. Some algae produce calcite or aragonite plates. Even plants form crystals, oxalate crystals in cells, sometimes as calcium oxalate. These biological crystals serve functions: protection, structure, storage. Biomineralization is controlled crystallization, organisms directing where and how minerals form. The result is materials stronger and more organized than simple inorganic crystals. Nacre, mother of pearl, is layers of aragonite plates separated by organic material, creating toughness and iridescence. Studying biomineralization inspires materials science, teaching us to build composites that combine organic and inorganic. Nature has mastered this, creating materials like bone, lightweight yet strong, or shells, hard yet layered for resilience. Biomineralization shows that the boundary between living and non-living is not absolute. Life uses minerals, shapes them, incorporates them. Crystals are part of biology as much as geology, participants in life processes blurring the line between animate and inanimate. Crystals erode, weather, and return to sediment, completing cycles. Crystals are not eternal. Exposed to air, water, and organisms, they weather. Feldspars break down into clay minerals. Quartz resists longer, but eventually fractures and erodes. Calcite dissolves in acidic water. Weathering disintegrates rocks, returning crystals to sediment. Transported by rivers, deposited in seas, sediments accumulate, eventually lithify into new rock. Minerals transform, metamorphose, melt, and recrystallize. The rock cycle describes this endless transformation. Crystals form, weather, reform. Atoms that were once in a mountain's granite may become sand, then sandstone, then, if subducted, melt and crystallize in magma, forming new granite. The cycle continues, driven by tectonics and climate. Crystals are not permanent, but temporary. Arrangements, stable for millions of years, but ultimately transient. This impermanence is poignant. Even the most enduring structures yield to time, yet it is also renewal. Atoms recycled, taking new forms, participating in Earth's ongoing creativity. Crystals remind us that nothing lasts forever, in fixed form, but matter persists, endlessly rearranged, forever becoming. The study of crystals is crystallography, a rich scientific field. Crystallography is the science of crystals, their structures, properties, and formation. It combines physics, chemistry, and geology. Crystallographers use X-ray diffraction, electron microscopy, and other techniques to study crystals at atomic resolution. The field has revealed the structures of minerals, metals, proteins, and viruses. It has advanced materials science, enabling design of new alloys, semiconductors, and pharmaceuticals. Crystallography is foundational to solid-state physics, explaining electrical, magnetic, and optical properties of materials. It is essential to mineralogy, classifying thousands of mineral species by structure and composition. Crystallography also touches biology. Protein crystallization allows structure determination, aiding drug design and understanding disease. The International Union of Crystallography coordinates research, standardizes nomenclature, and publishes findings. Crystallographers have won Nobel Prizes in chemistry and physics, recognizing contributions to understanding matter. Despite its importance, crystallography often works behind the scenes, unseen by the public, but essential to science and technology. It is the study of order, of how atoms arrange and why, turning the abstract into the concrete, making the invisible visible through the evidence of crystals. Crystals are patient teachers, revealing lessons slowly. Crystals teach patience. They form slowly, requiring time beyond human comprehension. They reveal their properties slowly, through careful study and observation. Understanding them requires patience, examining specimens, learning geology, chemistry, and crystallography. There are no shortcuts. Each crystal is a puzzle, its color hinting at composition, its shape at structure. Learning to identify minerals takes time, building knowledge of properties, testing hardness, observing luster and cleavage. But the effort rewards. Each identified mineral is a victory, a connection made between hand and mind, between earth and understanding. Crystals do not hurry. They wait in rock for millennia until conditions bring them to light. They wait in collections until someone appreciates them. They endure handling, examination, display. They are patient, and they teach patience. In a fast-paced world, crystals are reminders that some things cannot be rushed. Beauty takes time to create. Understanding takes time to build. Appreciation grows with patience. Crystals teach us to slow down, to observe closely, to value the gradual accumulation of knowledge and beauty, to recognize that the best things often come from waiting. In the end, crystals are Earth's art, created in silence. Crystals are art without artists, beauty without intent. They form according to physical laws, yet the results are stunning. Nature, through chemistry and time, creates works of aesthetic power that rival human art. The symmetry of a quartz cluster, the color gradients in an agate, the transparency of a diamond. These are masterpieces. They were not designed for our eyes, yet we find them beautiful. This suggests that beauty is not purely subjective, but has roots in structure, symmetry, and order. Crystals embody principles, balance, harmony, complexity within simplicity that resonate with us. They are Earth's art gallery, open to all who seek it. From the glittering geode to the towering mountain, from the humble pebble to the priceless gem, crystals display the planet's creative range. They are made in silence, in darkness, without audience, yet they emerge into light as objects of wonder. They teach us that art is not only human, that the universe creates beauty without consciousness, that matter itself, arranged properly, is aesthetic. Crystals are proof that the world is beautiful, inherently and abundantly, a gift waiting to be noticed. And so, dear listener, our journey through the quiet world of crystals comes to a gentle close. From the deep places where they form, grain by grain, to the light where we discover them, crystals have shown us the patience of Earth, the beauty of order, and the wonder of deep time. We have wandered through caves lined with giants, across deserts where geodes hide, into the hearts of mountains built from interlocking grains. We have seen how color emerges from impurity, how shape reflects structure, how hardness depends on bonds we cannot see. We have learned that crystals are both ancient and present, both common and precious, both simple and complex. They are teachers, gifts, and windows into processes we can only imagine. As you rest, here, letting your thoughts drift into quiet, imagine yourself surrounded by crystals. Picture a geode, its hollow heart lined with amethyst, each point catching light, glowing purple in the stillness. See a quartz crystal, clear and perfect, 6 faces meeting in precise angles, light passing through without distortion. Feel the weight of a polished stone in your hand, smooth and cool, shaped by time and now resting with you. Crystals have carried us from Earth's interior to this moment of peace. They have shared their stories, written in mineral and light, in form and color. They have reminded us that beauty is everywhere, that order underlies chaos, that patience yields treasures. Now, as you settle into rest, let the quietness of crystals hold you, their enduring presence a comfort. Close your eyes, breathe deeply, and drift into stillness, into dreams, into the deep, timeless quiet where crystals grow and wait. If you happen to still be awake, you can continue to the next video when you are ready. But if your eyes are growing heavy, let the soft glow of crystals guide you into sleep, into rest, into the silent peace where time moves slowly and all is well. Good night.